Okay, so good morning, everybody. So already you are here at the weekend for on the whole week, but so welcome to weekend. So it's a bit too late, but so as center director, I would like to introduce briefly our center. Okay, first of all, what is RIKEN? Already you are here for the whole week, and you have seen these Japanese letters. So these 6 letters are pronounced as Rikagaku Kenkyusho, and the first 3 characters, Rikagaku means physics and chemistry, and the last 3 characters, Kenkyusho means research institute. And previously, the English name of RIKEN was Research Institute for Physics and Chemistry or something like that. But nowadays, we have even more than that. We have biology, medicine, supercomputer, and AI. So the name has to be changed. Then, so in Japanese, okay, 6 letters are too long, and usually people don't use this Rikagaku Kenkyusho full name, but they pick the first letter and 4th letter and attach them. So this is pronounced as RIKEN in Japanese. So in Japanese, RIKEN is an acronym, and all people basically use RIKEN for our name. But in English, so at some point, the headquarters of RIKEN decided to use this Japanese acronym as our official name. So if you see RIKEN, it looks like Research Institute for KEN, but it's not true. So RIKEN is our official name. It's not an acronym. So that's the most important message today. So RIKEN actually has a relatively long history. So it started in 1917, actually as a private foundation. Even some emperor's family donated some initial funding. Then after that, RIKEN did a lot of great research in physics and chemistry. And they actually had a lot of companies and plants, like 63 companies and 121 plants in 1979 and 39. And it was called RIKEN Concern, and they were actually quite successful and big entity. Because they were so successful before the World War II, so it was regarded as a kind of dangerous entity. And after the World War II, RIKEN was broken up, unfortunately. But in 1948, RIKEN restarted as Scientific Research Institute. Then after that, we had 2 Nobel Prize laureates in physics, Yukawa and Tomonaga. Then later on, one of the president of RIKEN, Noyori, was also a Nobel Prize laureate in chemistry. So then now we are National Research and Development Institute. So we are completely public institute, so funded by the Ministry of Education in Japan. Then, so this is the kind of entire research organization of RIKEN. Okay, RIKEN has a 7-year term, and the new 7-year term just started in this April. So this is a kind of brand new organization. And basically, we have 4 research areas. So there are physical science, sustainability science, life science, and mathematical, computational, and information science. And in total, we have close to 2,000 researchers. So it's a big entity. And we are actually part of this mathematical, computational, and information science domain. And our center, the Center for Advanced Intelligence Project, AIP, is listed here. So then what is RIKEN AIP? So RIKEN founded the Center for Advanced Intelligence Project in 2016, so 10 years ago, under the Ministry of Education, Culture, Sports, Science, and Technology. And we have about 140 employed researchers, and more than 40% are international researchers, and about a quarter are female researchers. So we are quite diverse in terms of Japanese standard. Then we have 250 visiting researchers, and we have about 100 domestic students. Then also we are quite active in inviting international interns, and in total we had already about 200 interns. They were quite active working here. Then so our office is located in the center of Tokyo, luckily, but some teams are located in different universities. So from Sendai to Tsukuba, Nagoya, Kyoto, Fukuoka. So we are distributed. Then so RIKEN AIP was originally a 10-year project, started 10 years ago. So this is actually the final year of the first project. But as I said, RIKEN already started a new 7-year term, and our center was already extended. So this means at least in the next 7 years, we maintain the current structure and continue doing a similar kind of research. So we have 3 research groups. This is the final slide. So we have 3 research groups. And the first one is called Generic Technology Research Group. And here, so we try to do basic research on learning and inference. And also some people are working on statistical and optimization theory. And MT's team is here, and he has one of the most active teams in this group. Then the second group is called Goal-Oriented Technology Research Group. And here we have 25 teams, quite a lot. And so they are roughly categorized into 2 subgroups. And one is AI for science. So they work on like cancer research, material science research, genomics research. So these are quite active in Japan, and we try to kind of boost their research based on AI. Then the second half is working on AI for societal problems, because we are a public institute. We hope to contribute to society, and teams are working on natural disasters, elderly healthcare, robotics, and these are quite important topics in Japan. Then the third group is AI in Society Research Group. So the first two groups are more on science and technology, but the last one is more on the societal side. And they are working on personal data management, AI security, economy and management, ethics and governance, and topics like that. So three groups are quite diverse, and it's not that straightforward to have communication among groups, but we are doing our best. And also MT is actually quite active in mixing different groups, people from different groups. So hope that we continue this kind of open research style in the next 7 years, and you are also part of it. So we are continuing our research at least in the next 7 years. Hopefully we can have more collaboration with you, communication with you, and collaboration with you in the future. Okay, thank you very much, and enjoy the rest of the day.
Thank you so much for having me. Yeah, I was quite excited when I got the invitation email. I wanted to try to talk about something different than what I talked about last year. So we'll see how the talk goes. I feel like it's a bit vague, but hopefully, there's going to lead to some discussion and some thoughts, and it's going to be interesting. Before I get started, because I never get to my last slide. And by the way, like if you have questions, feel free to interrupt me. So I'm quite happy not to finish my slides because I'm not sure how useful the slides at the end are. So just ask questions as we go. And but before that, because I never get to the last slide, I wanted to do a bit of PR for COLAS. So this is a conference I started with Sharath and others some time ago, and the next edition. So this will be the 4th edition, would be in US, in Philadelphia. So yeah, consider coming. So we're trying to build a community. So some people see the conference as being just about continual learning, which is the theme here. It's not about that. It's about any kind of learning paradigm that doesn't fit the standard train test. So we're quite keen to hear about out of distribution generalization, transfer learning, unlearning, any kind of things. So we're open to all kinds of perspectives, from like a neuroscience perspective to, and then the goal is we think sort of this kind of questions about how to learn more efficiently is happening in small communities that are quite separated and are not communicating. So the main goal of the conference is really to connect people and to create synergies between this. So anyway, so this is the list of speakers we have this year. Yeah, consider attending, consider checking out the website maybe for next year. And I also put the summer school I organize every year in case any students are looking for summer schools. I think it's also like a great summer school. This year we're going to be in Sarajevo, so this is going through Eastern Europe usually. So if you ever want to see Eastern Europe, that could be a good opportunity. Cool. Just jumping into my talk. So I guess, well, I kind of struggle to figure out what my talk is about, but I think it's trying to look at a slightly different angle, maybe a more traditional deep learning angle than what MT might have presented previously, which is, I think in the end, what all of this is about representation learning and sort of the role of representations in how they do things. And my perspective is that maybe that really nice formula that MT showed doesn't say anything about the representation, so at least not straightforwardly, and it's a bit hard to see how representation comes in. And in my talk, I'm going to try to argue that we need to think about the representation explicitly. They're not just sort of like a side effect of the learning process, and you start learning and some representation come out, but like you need to think about them. And I think that's what the talk is about, but like let's see if we get there. And I want to, so this is, I was meant to put it on archive, I didn't manage to. So it's been a long time since I well, I was a first author of a paper, so this is one of those things. I at some point got obsessed about this idea, and I wrote a paper. It was more like a position paper. It really doesn't have any experiments. It's kind of vague, but it's trying to talk about the role of the optimizer, I call it, but the learning rule in learning. And what I'm trying to convey is that because we're in a non-convex scenario, the optimizer matters. So the path that you take in the parameter space matters. And even if you start from the same initialization, you fix everything else, the choice of optimizer will have a qualitative effect on the end solution that you have. So you might end up converging somewhere quite different. And this is not just, I mean, this can be qualitatively meaningful, right? Like you can exploit this, and this can have properties that you really care about. So basically what I'm trying to say is like, you know, we think about learning or optimization a lot of times from the convex point of view, and the convex point of view, no matter where you start, you converge to the same point. There's, you know, at the end of convergence, there's nothing about the initial conditions anymore in the system, like you forgot everything. In deep learning, that's not how it works. And you know, the starting point for this, for me, for example, was Belkin's work that at least the way I interpret it, so the double descent stuff, the way I interpret it is what he's trying to say is that it's sort of, it's exactly this. It's like what happens is when you blow up the model, you have certain minimas get closer to your initialization and you converge to those. And those are the minimas that generalize because they're close to initialization, so they're close to zero. So there's a little bit of that. Okay, and
I just wanted to.
Oh, sure.
I just wanted to make comments to Bayesians.
Oh, sure.
I think this is an amazing slide. Bayesians think that prior should disappear. You know.
Right.
So this is weird. You know. This is weird.
Yeah.
And we need to think about this.
Yeah. So the prior does not disappear in this case.
Like in MCMC, you're trying to forget where you came from, and here you cannot do it.
Yeah. Yeah. Thanks. Yeah. That's. So actually, I mean, in previous talks that I have where I kind of touch on this topic, I have usually this figure that I've copied. I've put it everywhere. I think that looks like a rabbit. I'm not sure if people would agree, but that's sort of my one slide where I'm trying to say that like the way we should think about like what's going on. I use this slide to talk about expressivity versus learnability because I think that's another big issue. So every time we talk about neural networks, we end up talking about expressivity, and we're trying to say, well, this architecture is more expressive than that. And sort of my point is expressivity is interesting, but at the end of the day, it's not what's going to limit us. And I think we're seeing that more and more. And kind of diverging a little bit, but just to give you like the usual sales pitch that I do is this like really old work from Hava Siegelman that talks about Turing completeness and says, well, recurrent neural networks are Turing complete, and there's a lot of excitement about them. I don't have a proof, but I have a hypothesis that the recurrent neural networks you can reach by training them with backprop through time, that set is not Turing complete. Actually, you can never reach a lot of interesting kind of behaviors of recurrent neural networks. And I'm even going to venture and say that the kind of nonlinear recurrent neural networks you can learn are probably not more expressive than linear recurrent neural networks. So it's actually the amount of expressivity that you can get from them, it's extremely limited. And the way I kind of describe this is saying, you know, that you have sort of H, which is sort of the class of functions you could represent with your particular choice of model family. But then you have what I call the reachable H, which is sort of the functions you can actually reach by whatever choice of optimizer you have. And that will depend, obviously, on the data, that will depend on initialization, but would also depend on the choice of optimizer. And I guess sort of the new twist that I was trying to push in this archive paper that's not out yet is that this is actually exploitable. But yeah, question.
Okay. So
it's not on.
Just press it once and about the expressivity versus learnability, right?
Yeah.
So, do you think this reachability is the property of gradient descent itself, or optimization algorithm?
So I think any choice of optimizer would have a different kind of reachable set, and like even gradient descent is too vague, right? Even
is this like a limitation of gradient descent? Is it even a limitation of gradient descent?
Not really. Like even if you say you'd have a magical optimizer that can get you to a global minimum, like in neural networks, you have exponentially many of them. So then which one do you go to? I mean, actually, the current claim is that HDD gets to a global minima. It's just there's so many of them and they have so many other properties in terms of test and valid. So I think neural networks is a weird enough space that there's no choice of optimizer that doesn't need to make a choice. I'm using the word choice too many times, but whatever you pick, it has to make a choice because it's like an exponential space of solutions that are, from the training perspective, equally good. From the generalization, OD, or other kind of perspectives, they're quite different between them. And then that's where the inductive bias of the learning approach comes in.
Well, just a random thought, like, does it make sense to switch the optimizer on the way, because we know the different optimizers have different.
I mean, it could. I think at the moment we don't really understand this reachable set, so I would not know which one to argue for. But yeah, you can imagine it. So yes,
I think the idea of kind of characterizing the reachable set, right? Like basically dynamic unloss functions.
The mic's not working.
Sorry, I'm just not holding it.
Yeah.
Okay, so I think it's super interesting, right? And I think it definitely goes to your point of there are equally okay solutions, right, in terms of non-convex loss landscape, and then which one you go to because your task essentially what you're saying is underspecified, right?
Yeah.
You're like, I want to classify A really good, secretly in the future I want to classify B, C, and D, right?
Yeah.
So things that are equally good for A may not generalize well to A, B, C, B, and C, and D, right? So I feel like, choosing, I really love this, by the way, because I want to understand optimization trajectories better. But so like, there's one way of approaching this where you go, okay, let's for each optimizer understand the reachable sets, right?
Yeah.
There's specific dynamics,
Yeah.
super interesting. And then maybe like, I don't know if this is more Bayesian, but more sort of model-based way to say is why don't we characterize the intermediate representations that we want, right? So instead of saying, hey, these two random restarts gave you two representations that's equally good for classification of A, but this one generalized better as B, right? But why don't we say what task we want to solve so that we can specifically specify that sort of representation, right? And then you do get a lot of that with a semi-supervised sort of BAE and representation engineering, that sort of stuff, right? Yeah, it's a philosophical.
Yeah. No, I totally agree. I mean, you'll see in my talk that I switch between talking about representations to talking about this stuff, and I kind of like switch between back and forth. I think what I'm trying to argue more about is that like we don't have the tools to describe these things, and we don't have enough research. Like if I'm looking at, for example, for like expressivity kind of works that are talking about like what different models can do, you can find lots and lots of works. If you're trying to look at what kind of functions can I learn, you'll find very few works in the literature. And we don't even, like for expressivity, we have this kind of things where you say like in the limit as this model grows, you can do this we don't even have anything like that in this space. So I'm just trying to say, well, we should do a bit more research on this. I try to do that proof that I said that RNNs can't really be Turing complete if you consider it's not easy. Like I realized as soon as I thought like, oh, this will take me like a day. And I started writing things down and no, it doesn't work. Like it's somehow complicated, but I think it should be doable. Yeah.
Regarding the reachability, should we also take the computational time into account?
Exactly. Yeah. Sorry. Yeah. The way I used to say this is like basically anything that we do affects the solution, like from the amount of training steps that we pick, like anything, the device, we have so many. I was talking to a hardware person, and we know this, like when we train these big LLMs, depending on the choice of hardware that you pick, you get completely different solutions. And, we have like, oh, for this model, you should not train it on this generations of TPUs because it's not going to work. Like you need to train it on that. And this is all like numerical precision that somehow affect the optimizer in ways that it seems like we can't undo. Like it's not like, oh, I know that this rounds things this way, that rounds, and I can do a correction to my optimizer and it's going to work out. Like people have not managed that. So we do, like when we internally, for example, at Google, when we have models, we also specify on which family of TPUs they were trained, because that has an effect that we don't fully understand, and it's important. And if we just want to reproduce things, it's like you run on that generation of TPU with that and that specification. So anything we touch, specifically at scale, ends up having an impact. And most of the time we're kind of ignoring them, and we assume like it's going to be in a epsilon radius. I guess what I'm trying to argue is that it would be nice to understand if we can exploit them instead of just deal with them. So that's kind of the goal.
Yeah, I mean, the algorithms we used 20 years ago are maybe not so different from the ones that we use now, but now we can, because we have much more compute, our reach has become much bigger. So maybe it's less about the optimizer, but also how much compute you throw.
Yeah, that's a fair point. I mean, the other thing that I wanted to say, and then there's a sort of this another reason to care a lot more about the optimization side of things is because I feel like because of scale, like if you pick enough transformer, like even though you can show that there are certain things you can't represent with transformers, so I still believe that there's weak spots, there are region in the functions that you can't really represent with a transformer no matter what you do. The expressivity of this class becomes large enough that really the bottleneck I feel in a lot of things that we see, it's really coming from the optimization process. Like if I go to the 100 billion size transformer, it's not the architecture anymore that is really bounding me. It's more about everything else. Data. I mean, everyone knows this, right? Like we have workshops about this. So that there's this data-centric view on machine learning. So I think Mihaela van den Schaar and others were pushing for that. So that's one side of this. So like people are just saying the only thing that matters is data. What I'm trying to argue is just data. It's also the optimizer and the compute budget and so forth. But these things now matter a bit more than the architecture just because the architecture is big enough and expressive enough. Unless you want to do something quite specific, and then I'm happy to argue that the architecture can't represent those things, but that's a bit more. Okay. So I wanted to provide some test cases. So I think actually from my discussion with MT yesterday, he has a much better explanation of this. My explanation is very vague, but the first case that I wanted to show is like what happens if you do a second order optimizer versus a first order. But actually, it's not, in my mind, it's not even about the second order method. It's really about a non-diagonal preconditioner. So what happens? So it's a standard thing by now. We never use a full matrix for the preconditioner. It's too expensive. No one sees any benefits. There are some few folks that are still doing research on that side. And they struggle, and I wanted to give them a different reason of why you might want not to do a diagonal thing. And the intuition that I had, and this is super vague, is that in a second order, in a non-diagonal preconditioner, you're really looking at how different weights affect each other, right, through the off-diagonal elements, and that helps you to avoid some kind of overcounting, and basically eliminates kind of wasteful movement. I mean, we have enough papers, like for folks who know, like Path SGD, was a paper like this where you're trying to argue that SGD moves in this direction that actually don't affect the loss, and it's a lot of wasted movement. In the same way, gradient descent, because it's looking at each parameter independently, does this sort of wasteful movement. And I think what this does, it basically makes your representation occupy more volume than it needs to. If I'm thinking of this from a geometrical kind of point of view, there's some like thin space where, that would be the minimal representation that you need to do your task. But now, because I have all of this noise in the process, I'm basically moving away from that small subspace and I'm occupying more and more volume. And I was trying to kind of, make SGD look like something noisy and second order like something not noisy. But I think there's maybe a better way of explaining this. But like we actually run some stuff just to see if anything holds true, and you observe this. So what you observe is that the representations you get if you run a non-diagonal, like kind of expensive. So this is small models. This is MNIST. This is not anything impressive, but because it's small, it's MNIST, we could run. I mean, we ended up running shampoo, but like you could run whatever you want. But shampoo is a non-diagonal thing, right? We try to keep it as full as possible. What you notice is that, so I need to explain the results. So first of all, the empirical results is if you just do fine tuning, one task after the other, using a second order optimizer with anything, nothing continual learning specific, and you look at the amount of forgetting, purely just amount of forgetting, by the fact that you use a full matrix, you forget a lot less. So there's it's nowhere near, say, I'm going to use EWC or any on a fancy method. So we're not saying, oh, I can just switch to a second order optimizer and I don't need to do any of the continual. It's not there yet. It's going to break. But there is a significant difference where you see the amount of forgetting is just less because you use a full matrix preconditioner compared to using a diagonal one. And then what we did is we look at the covariance of the representations of the layers. So this is an MLP. And we're looking at the spectrum. And what you can see, I guess, is if you have a full a non-diagonal preconditioner, you have a lot less number of meaningful eigenvalues. So you have a lot more eigenvalues that are close to 0. So basically you're operating in a subspace of your model. So you're learning in a more compressed representations because you're not using the entire space. And we do visualizations that are kind of arguing in that direction. So this was kind of the observation. So the way I was framing this is that you learn more localized representations. We're not making a claim whether that's a good thing or a bad thing. Actually, that could be a very bad thing. Like early deep learning mantra was you want distributed representations that take as much volume as you can because you want to be redundant, you want to be robust to anything. Second order methods seem to learn a much more localized representations, but if you want to do continual learning, like localized representations are useful because they take less space, so you can learn more. If you want to do compositionality, there's been a big issue. If you think about compositionality, the first step in order to have something that is compositional is you need to localize your representation so that you have sort of the elements that you want to compose. If everything is distributed, at least to me, it's really hard to. I think this is like a place where the number theory thing can come into play. Like there is like when you think about compositionality, there's this like compositionality makes sense when you talk about discrete objects, but representations are continuous. So I always struggle with how do I go from continuous representations to like discrete concepts like compositionality, which seems to be at the core of generalization. So I feel like that's a very interesting theme of like, what is, because in neural networks, we don't know how to do discrete representations. We don't know how to work with discrete variables. There are folks who work on it. It doesn't work. Like everything has to be continuous. But then a lot of our intuitions are actually about discrete objects. And it's always been a really hard thing to try to match these things together and make them work together. So any help in that space would be useful.
So you said you did, sorry.
So, yeah.
Just a question about how exactly it was done.
Okay.
So you said fine tune with a method. I didn't understand.
With shampoo in this case, just a second order method with
So you have a pre-trained model or something?
No, this is all from scratch. This is like a 100 hidden units MLP trained on permuted MNIST, and the other one is on class incremental MNIST, again an MLP trained from scratch.
Keep learning.
Just keep learning.
Without any like EWC or anything.
Yeah.
Just keep learning.
Without any signal, just learning one after the other.
Okay, thank you.
And then just to continue kind of, because last year, at least at the workshop, it was a huge theme around plasticity and plasticity loss. I mean, it's still a big theme in continual learning. I talked somewhat about this work from Claire last year as well. But there is this view on plasticity that it's gaining more and more momentum, and Claire is kind of the person that I would point to if you want to talk to someone about this, of plasticity really being just ill conditioning of the optimizer. And a lot of, I mean, there's the extreme case when you have dead units, but really if you're just have better optimizers that deal with the ill conditioning of the optimization problem, like you just don't end up in that regime anymore. And as an example, we had this algorithm that we call NAP, if I remember, but it's really just adding layer norm and weight projection, weight standardization. So where you project your weights to be on the sphere. These are both techniques from optimization that they do them in deep learning quite often. We just need to put them together, and then you need to realize that, which is a surprise for RL folks, you need to realize that for Atari, you actually need a learning rate schedule. So RL folks always think that a constant learning rate is all you need. Actually, what's happening is that they have an implicit learning rate schedule that is hidden in sort of the dynamics of the learning of the neural network, because the norm of the weights grow and the way everything works, it turns out you have a decaying learning rate schedule. So once you start using fancy optimizers, you need to be explicit about your learning rate schedule. So you need to add that on top. But again, for an optimization person, these are tools that we always use. Like if you talk to someone working on optimization and supervised learning and you tell them that you don't have a learning rate schedule, they would say you're crazy, right? Like you cannot get anything good without a learning rate schedule. So anyway, you compose all of this, you get this algorithm, and then on standard plasticity loss kind of benchmarks, you see it does quite well. And it kind of highlights that plasticity a lot of time, and the work has a lot of inspections, trying to highlight that it's all about ill conditioning of the optimization, that it's really what creates this loss of plasticity or inability to learn, which maybe is not as surprising. And then we have this more recent work, I wanted to highlight it. So again, they're showing how the optimization kind of affects qualitatively sort of the whole process. So here we argue that another way to view loss of plasticity is basically the fact that the system gets stuck in this lazy learning regime. So there's lots of work that talk about grokking and say that grokking is just sort of when the system groks. So for folks who don't know, grokking is the specialized scenarios where you train an LLM and you get perfect training accuracy, not training loss. And people don't talk about the loss, and that creates problem, because if you have perfect training loss, then nothing happens, right? The gradients are 0. But you have perfect training accuracy and chance test, and it stays like that for a while, and then suddenly the test goes up, right? So there's this moment, this aha moment, and the system figures out and starts working. And there's been works showing that this is really like, when that happens, it really happens because you're switching from a lazy learning regime to like a future learning regime. And this is all about signal propagation. So the issue is like the signal doesn't flow correctly through the network, and that's why in this lazy regime, and then just certain layers learn. Once all the layers start learning, everything starts working. And we're arguing that this is exactly what's happening in plasticity loss as well. So that's another way of viewing the thing. And in particular, like one thing that works for grokking is to reworm the learning rate. So we tried reworming the learning rate, and and again, you get huge boosts by doing this kind of cyclic reworming learning rates that kind of show, again, that it helps, with this kind of loss of plasticity, which, yeah, sorry, there's a question, so.
Yeah, I didn't want to interrupt. So you mentioned with grokking the distinction between perfect accuracy and perfect loss.
Yeah.
And I think that's really important, because like you say, when you've got perfect loss, then there's no
signal.
There's no gradient signal anymore.
Yeah.
So do you think that with grokking, you always end up reducing your loss when you grok suddenly?
So to be honest, I have not looked that carefully. I would imagine. I would be surprised. Like, unless you're doing something stupid with your learning rate, the optimization should do only one thing, which is reduce the training loss. Like if it doesn't do that, then it's everything is awkward. That means that like you're just taking like a random step in your, which I don't think is happening. So really what I think is happening is your training loss is always decreasing. Maybe there's a plateau, so it kind of doesn't decrease as fast as you want, but it's always decreasing. And it's just a point where you can't decrease the training loss anymore unless you start learning features. Like you fitted the thing as well as you could have in this.
Then it's a capacity thing, right? Your network is too small to fit your data without learning better features, right? Because if you make your model even more flexible and add more parameters, then you should be able to fit your training data.
Possibly, I would disagree in the sense that like you have to think of like when you're training, you also have this implicit, like even though most of the time you do have an L2, sometimes you also have you have the L2, but you also have the implicit regularization that is coming from the architecture. So there is, like you could potentially, like if you have no regularization, you could say that like, once if I have enough capacity, I can get 0 error and I'm done. But because you have this regularization, it's a slow process, but you can realize that, I can get a solution that gives me equal performance on predicting these things, but has smaller norm. And I'm going to go for that. So basically, I'm just arguing that like you need to include these regularization terms when you're thinking about the loss surface, and it's a different kind of loss surface, but yeah.
Similar question about sorry, can you go back?
Yeah, sorry.
Yeah, so similar question about like, grokking, why does it happen, right? So I feel like I'm struggling with your explanation, which totally makes a lot of sense, which is about the architecture itself, like, and how like signal propagates amongst different layers, the choices that, but to me, when we say characterizing the set of feasible reachable functions, what is the inductive bias of an optimizer? I always tend to think about characterizing dynamics on the loss function landscape, right?
Yeah.
Because you're like, well, if you train long enough, all of a sudden I can learn to grok, right? But why do I have to? right? You know what I mean? It's there's like I feel like that middle part where I all of a sudden learn that I can do this task with a better representation has to be explained by the loss landscape geometry or not?
I kind of, in spirit, I understand what you're trying to say. I think it's a well, not a mistake. I think there is a tendency for lots of folks to like abstract away the neural network and just think about the loss surface and think of it, oh, there's a function, there's some loss, and I'm working on it. I think it's a mistake in the sense that you really need to think about the architecture itself and kind of think about, like, I guess I mean, really what is happening is, it's kind of hard to explain. So if you really want to think about it from the loss perspective, you could argue, okay, there is a subspace that's representing by the lower layers, and really what's happening is I'm not moving in that subspace. And you know, it's like reachability is basically saying that as long as you're not exploring some axis of your loss landscape, you're not going to do well, or something like that, and you're going to end up. But it's a little bit hard if I'm just abstracting everything away.
I agree. Then you've lost the whole kind of what can the concreteness of what's happening.
Yeah, like all axes should be equal, right? Yeah. And it's like, why does it matter if I'm not moving on this axis and I'm moving on that? So I think bringing back like, for example, all this kind of like signal vanishing kind of phenomenon, like we would never get them if we're just thinking of the model as F and we're minimizing it. So yeah, but I see. Yeah.
I guess I was arguing for maybe kind of like, and that's also my general, like, you know, kind of complaint about like, you know, neural network theory. Yeah. Like it doesn't actually deal with the practical, right? So, but like, I mean, isn't there kind of like a connection that we can make? I agree, loss landscape.
Hopefully.
But this is like, I mean, I'm struggling with the intuition of why does it happen? Why is there a flipping point, right? Like,
oh, okay. Why is so we have some work that got rejected from, well, there's some work that's on arXiv that might be a little bit relevant. And there's actually work from some folks from ETH that is in the same spirit. So like one thing that we've noticed, and maybe has something to do with this, is that the first, like when you're trying to minimize some loss, let's say it's a classification task, the first thing that the neural network is trying to do is to maximize the norm of the signal that goes into the magnitude of the logits, because then that helps you minimize the loss somehow, and the softmax helps you there. And like one thing that we've noticed is if you have W1 times W2 and you're trying to maximize the output of this product, funnily enough, what happens is that there is, at least from the dimension, this is pure empirical, I have no theory, but empirically what we notice is that the weights are changing in such a way that the eigenvectors align with each other, at least the largest, the eigenvectors corresponding to the largest eigenvalue. And then as soon as that alignment happens, then all the learning goes on that eigenvalue. So, I mean, this connects to the work of Andrew Sachs. If you know, the whole exploration of deep linear models that says that like you're kind of learning, one eigenvalue at a time. So there is this dynamics where if there is a path to increase norm, the learning is just going to focus on that for a while until it's not able to minimize the loss anymore by doing that. And then it starts looking at the small eigenvalues and starts kind of expanding. And it could be that there's something similar here where like, oh, okay, the first layers, they don't really need to move because, but yeah, there was a question, yes.
One more comment if you don't mind.
Yeah, sure.
Thank you. Maybe I would like to offer an additional explanation.
Oh, perfect.
Theory about, in terms of graphing, there's theory about that looks exactly at the relationship of the norms between layers.
Yeah.
And that's super crucial for understanding the speed in which they are.
Yeah.
And essentially what's happening is that, I think you also said something like this, so that the last layer is able to learn relative to the other layers. So the other layers are not learning yet, so you don't really learn a helpful representation for some time. But because of the implicit bias or L2 regularization, this relationship between the norms is changing over time. So your training loss, by the way, is already 0, roughly. So there's nothing that happens, but because of the implicit bias and L2 regularization, you still change the norms. And at some point, the lower layers also start learning. And once you start learning the features, better features, a better representation, now you can generalize, because what's actually changing in graphing is that your training loss goes down already very quickly and early, but the generalization loss doesn't. But later on, the generalization loss kicks in once you can learn relevant features.
Yeah, no, I totally agree with that. And, you know, I don't have it on the slide, but I think her name is Clementine, like Andrew Sachs and people in his lab, and Clementine, I think, is the first author. She gave a talk at DeepMind. They studied deep linear models where they play with the norm of different layers and show all this kind of dynamics, and argue that all that matters is the relative norm between layers and the absolute magnitude doesn't. So, but yeah, like usually if I want to go in trying to understand this kind of dynamics, Andrew Sachs is kind of the person I usually look at his what he published lately, and he always has some interesting work in this space. So if you're interested in this kind of things, I recommend sort of checking out his publications as well. He's sort of an amazing researcher. Okay, so I wanted to give another test case, and then hopefully I'll see if I'm going to talk about ICL as well. So ICL is meant to be yet another kind of learning regime that has different biases on. That was the point. But another thing is, we had this paper before that I really liked, not necessarily for the reasons why it was published, but we had this work on power propagation where we were trying to do sparsity, but we were approaching it differently. So what we were trying to say is that you can reparameterize your model by raising your weights to some power. And the point of that is that if you look at the loss surface now, you've introduced a saddle for each weight around 0. And then the idea is if you learn, you get stuck in the saddle. So weights that are close to 0 will not be able to move away. So the model needs to use the other weights to do whatever it does. And this works surprisingly well, and it helps a lot in continual learning as well, because it forces you to learn compressed representation and so forth. The paper is from 2021, so it's been around for a while. It's an okay paper, but like the one thing that it's awkward about the paper is that actually it's a very awkward reparameterization. So the issue is if you reparameterize and then you use Adam can actually navigate these plateaus very easily, and then you don't get any effect. So what we had to do is we had to use a special optimizer that is more like gradient descent, but it uses a bit of preconditioner because otherwise you don't get good results. So we have a whole section of how do you even optimize this thing. But alternatively, what I realized afterwards is that you can get rid of all of that, and you can just say I'm doing gradient, or I'm doing Adam, where I multiply an additional preconditioner to my preconditioner. I'm composing the preconditioners, where my preconditioner is just W to the power beta. And this has exactly the same effect, right? Now, if I'm looking, because of this preconditioner, if I'm looking at the effect of the preconditioner on the loss surface, it's creating these plateaus again. And then I have the same effect that you end up with sparse solutions, and this is elegant. Like you don't need any machinery, you can apply it. You don't need to go into the network. You don't need to do anything. And again, it's just saying that the choice. So the way I'm thinking of this is basically what you can do by using the preconditioner. You change what it means to take a step in the parameter space. It's almost like I'm now going to use terminology that I shouldn't, but it's like playing with the metric of the space, right? And you're changing the geometry of the space, and now it's harder to move in some direction than others. So the point is, like, another way to regularize models is instead of changing the loss surface, by just playing with the metric, by just making certain directions to move slower than other faster, you're not changing any of the critical points. But by doing that, you can make the optimizer prefer certain minima than others, because what you're doing is you take certain minimas, you push them closer to you, and some you push them further. And we know that SGD is lazy and converges to the closest thing it can get to. So I'm just, highlighting that as like another way of thinking about regularization is by just kind of changing the geometry of the space by trying to pull things in. And the other thing I really wanted to have this example is, because here, I don't even know if this is true, but here I'm thinking of this as like I'm exploiting duality between learning algorithms and architecture design. Whatever architecture design, there's an equivalent change in the optimizer that would give you a similar effect, and I wanted to use the word duality somewhere. So this was like the place I could do that, because I'm exploiting that, and usually like you can go to many of these things, and you can like people really like to think about architecture design, and they put a lot of, but a lot of the inductive biases that you put in architecture design, there is an equivalent that you can potentially do in the learning, and sometimes that equivalent is much harder to frame and to do. Sometimes it's much easier. In this case, it's actually easier to do things in learning, but we're preconditions to think about architecture design. I mean, when we did the paper, we never thought about learning. We thought like, we need to change the architecture in order to get sparsity. We don't have to change the learning. So I'm trying to argue that the other thing is also working. Okay, now question, I'm gonna jump in context learning. I might need to skip some slides, but yeah, I wanted okay, so some of these slides are borrowed. So most of these slides are actually borrowed from Johannes. We did a tutorial on in-context learning. So, in-context learning is really seen as a new thing, and everyone is excited about it. I like to bring up this kind of thing. So first of all, I wanted to say that in-context learning is not really new. It's not something that emerged with LLMs. And you always find a paper by Jürgen that talks about it, but there's also papers not by Jürgen from 1999 that describe what is exactly in context learning. So if I'm not going to read it out, but like the thing in yellow is basically the same behavior that in context learning has. So, this was something that people have thought about it for a long time, from the 80s, and so the only thing is terminology, right? So the terminology that people used was meta-learning. Sorry, I can go back. So the terminology that people, I'm going to share the slides, but the terminology that people used to use was meta-learning, and in context learning is just a form of meta-learning, and particularly meta-learning is also like split in all kinds of variants of meta-learning. This is one categorization of it. And in context learning is kind of some memory-based meta-learning. That's what we used to call it some time ago. And there were at some point quite a few papers in this space. Seth Hochreiter had one, Jane had one, and so forth. There was the OpenAI one that I forgot who were the first authors. I think when people think meta-learning, they think of MAML, but that used not to be what meta-learning was about. It used to be a very big space with all kinds of different things. And in-context learning somehow is part of it. Yeah, these were some papers that are in that spirit. So the RL2 squared was the OpenAI paper. I'm going to try to skip because I'm kind of behind. And then there's also theoretical work, and I'm pointing here to Pedro's work because that's the one I know better. I was slightly involved in it a little bit. That is kind of, and it's a very Bayesian paper, so that's why I was just slightly involved in it, because there's parts of it I don't understand. But there is a sense in which, and this work is trying to show that if you have a system that has memory, I guess that's one way of framing it, or if you have a system that is conditioned on information, meta-learning has to emerge. So this is not a property of transformers. This is simply a property of a system that has memory. If a system has memory and it sees the right data distribution, then you're going to get something like in context learning. And this was, I'm just bringing this up because I remember at some point if you look in the literature post LLMs, once we, for example, introduce state space models like the new linear RNN stuff, people were asking, oh, can this architecture do in context learning? Oh, can that architecture do in context learning? And the answer is yes, any architecture can do in context learning. I mean, this is not a question. We knew this, and there's theory of why this is happening, but people keep asking, is there something attention specific and softmax specific? At the same time, I don't want to be too aggressive and say, well, why do we call this a new thing? There are good reasons for it. I mean, we did this with that deep learning, and it helped a lot. Sometimes it's useful to reinvent things and rename them just to kind of get a different perspective. And there are some specific aspects of ICL, right, that are transformer specific, and then somehow that can help us predict the behavior of these systems. And because we tend to use transformers a lot, this kind of transformer-specific aspects are quite important. So, I mean, it's always useful to remember that it was there before, but it's also okay to do that cut and say, well, this is a new thing, and it's a much more specific thing. Okay, I'm gonna go through. So I think a lot of you might know this. So but I'm gonna quickly go through it. So in particular, what I wanted to claim is that ICL in transformers has a lot of ties to gradient descent and learning in general. And that's why it's kind of interesting in the end when you see that the kind of representations, not necessarily representation, but the kind of behavior you get from them is quite different. And hopefully I'll get to that point to show some examples because that's interesting. But it's useful to try to understand, okay, how is it happening in ICL? And folks that are focusing on mechanistic interpretation, which is a big theme now in explainability, have been looking at transformers and weights of the transformers to try to understand how some of these things happen. And these are the slides. So these are Johannes' slides. So mechanistic interpretation is sort of the idea of coming up with a hypothesis of how it happens, and then it's kind of like a neuroscience-inspired thing, at least in my view, where you're trying to do exactly what neuroscientists do to the brain. You come up with a hypothesis and you start poking around to see if that is happening. And in particular, like in the mechanistic view of ICL, people have looked at the transformer and they kind of identified two things that they think somehow affects this behavior, and that is the positional encoding and the multi-head self-attention. And by far, most of the mechanistic work just looks at these two things and they kind of ignore everything else. I think long term that can be a mistake, but it does feel like a lot of things somehow, boil down to that self-attention layer. And yeah, this is just sort of how the self-attention layer works. Okay, so I'm just gonna skip from some of this. So the starting point of a lot of this work started from this work of induction heads. I mean, this work was kind of quite impressive, and a lot of folks kind of got obsessed with it. So the induction head was trying to explain this ICL behavior that was observed previously in I guess some variant of ChatGPT, the first one that came out, and they were trying to argue that what's happening is that the attention layers are kind of collaborating together to make this happening, and they say that the first attention. Okay, so I'm not used to this line by line kind of thing. I usually like to see all the slides, but the first attention head is trying to group information. So I guess in cognitive science or in neuroscience, they call this the binding problem, where you're kind of trying to bind the relevant information together. So they're kind of trying to copy together the tokens that are kind of related to each other. So that's what the second layer does, and the first attention layer does, and then the second one is just like reading out the information. So you do kind of like a k-nearest neighbor search with k equals 1, where you're like, okay, you have a question, you're looking for the token that's more relevant, and then from that you copy the element that was binded to it, and that's your output. And so there is this kind of very discrete kind of behavior of these two heads working together. So I guess this is a one-by-one showing. So if this is what would happen, you'd have a dynamics like this, where you would take these two parts and you'd group them together. So you'd get sort of this kind of pairing of xi minus 1 together. So that's the first head. And then the second head basically just does the search and then copies the element attached to that. So it does the search by half of the composed token and then retrieves the other part. And they did a lot of like poking around in the model, and they really see this sort of very sparse weights and this kind of very clear-cut behavior on these kind of simple models. And this initial work, I guess a lot of people kind of start thinking about how the attention work and how in-context learning works is more as a kind of k-nearest neighbor kind of behavior. And this is just a slide, so this is all from the paper showing that you really need two heads. One single head does not help you. If you have more, it doesn't do anything, because two heads are enough for you to copy the information. So it was kind of very clear information, clear kind of proof of what was going on. This is just a summary of what I said before, so I'm going to try to go through this a bit fast. But then, people start looking into this more and more. In particular, they looked at linear regression problems. So I guess this is what the slide was trying to say. So you can try to formalize this, and the first problem was kind of discrete in nature and kind of made sense to behave that way. Now they say, okay, let me try to do in context learning to predict sort of some function. And then they noticed something quite interesting, which is that the system did not behave like a k-nearest neighbor anymore. Like the k-nearest neighbor does not perform well on this task. Softmax performed quite well. And actually what people noticed is that it performed kind of on par with what gradient descent might do on these tasks. And then that's kind of started all this thing of like, oh, maybe it's actually doing gradient descent. So the alternative view now is that the first layer is copying things together to kind of build a data set, and then the subsequent layers are doing something similar to gradient descent to learn on that task. To kind of show that this is possible, what people have done, so this is Johannes' work, but other folks as well, is that they just remove the softmax so that you can do analysis and do math. And then once you remove that, you start with saying, okay, if I don't have the softmax, how would I write gradient descent in this? they come up with the formula, and then they checked whether the learning system does exactly that. Okay, and basically what was surprising to me when I was talking to Johannes back then is if you train from scratch small models and you're trying to look for this, you learn these super sparse weights. And if you look at them, you can actually read out that formula of gradient descent. So for like a 2-layer attention that you're trying to learn these linear regression tasks, if you try to learn them by gradient descent in a normal way, you really learn exactly the solution. And I think this is a surprising part about this kind of interpretability work. So then, Johannes had this work and then follow up where you can kind of show that, like, yeah, the in-context learning really behaves like gradient descent. There is a gotcha there, which is we thought that if you add a 3rd layer, that would be like an additional step of gradient descent. It turns out it's not. So it turns out that actually if you have 3 or more layers, the model does like a gradient descent plus, and it's actually surprising that we were even managed to figure that out. So it does 2 things. It's trying to whiten the inputs, and then it takes a gradient descent. So it's almost like a preconditioned gradient descent, where the preconditioner is something like the covariance of the inputs, where you can connect that to the Fisher if you want and all of that. So you kind of know why that is helpful. So it actually does even something slightly better than gradient descent if you have multiple layers. But it's really nice that you can really dig into it and interpreting this way. And these are all kinds of plots that are trying to convince you that that's true. That I'm not going to go into it, but these are just sort of comparisons of how a transformer does it versus how gradient descent does it, and those curves always kind of fall on top of each other. So it's kind of convincing result. Sorry, but at the same time, like I want to emphasize that it depends a lot on the data distribution, which is very frustrating. So like you can have a transformer that behaves like a KNN for some data and behaves like gradient descent for other. And sometimes you can have the same transformer, and if you give different queries, it will behave differently. So I think there's still a lot that we don't understand about it. It's just what we can say is that we can induce gradient descent-like mechanisms, and we can induce KNN kind of mechanism, but we can't say it does just one or the other. It might also do something in between. That's one thing. The other thing that is, sorry, yeah.
Did I understand correctly that the gradient descent comes from linear attention and the nearest neighbor is with softmax, or?
Yeah, so this is exactly the next slide. So the whole gradient descent story that people, okay, so the softmax models, if you look behaviorally wise, they do not behave like a nearest neighbor when you have this kind of regression task. They behave like some kind of gradient descent. The issue is we can't see that in the model. Like because of the nonlinearity, we can't really decode of like how does it do gradient descent. But in terms of like how quickly it decreases or what kind of performance it gets on linear regression tasks, it's on par with variance of gradient descent. If we get rid of the softmax, then we can actually identify the solutions in the architecture, and we can show it looks like gradient descent. So that's kind of where we are. And then, there's this claim that maybe the softmax ones try to use the linear part of softmax, which I don't even know what that means, but they're like, maybe it kind of linearizes the softmax somehow, and there's some region where the softmax becomes like, but like to me, I don't know, softmax is, if it was a sigmoid, I would have understood what it means. For softmax, to me, it's a bit overwhelming to understand what it means to linearize it. But it does somehow behave like that. The other thing I wanted to say is that, yeah, so basically, all of this analysis is done with linear attention, and that can be a bit of a downside, because with linear attention, we have a lot more certainty that it behaves like gradient descent, but then linear attention does not work as well as softmax attention. But I think this is like a very active area of research, and actually it turns out that linear attention is the same stuff as linear recurrences, which are quite popular. And actually, so this is from a work from gated delta networks, where they just take a bunch of SSM architectures, so this kind of linear recurrent neural networks, and they show that they're all like minimizing some kind of linear regression. Like you can decode whatever the recurrence is to some, and then this creates sort of like a really nice area of research, because now you can come in there and say, well, I'm going to use this loss, and I'm going to have this regularizer, and what recurrence do I get? And a lot of new architectures is just basically that. People coming up with new losses, new regularization, coming up with new architectures. And MesaNet is an architecture I was involved in, is exactly that, where basically what it tries to do, it's still an L2 loss, but it tries to solve it in closed form at each step. And like we're basically starting to get to a place where there is like more and more the transformer and this kind of linear RNNs are on par. So basically, yeah, I guess the linearity assumption seems problematic. It does feel like sometimes it can work in the sense that we can get these sort of linear RNNs to perform very close to transformer in most scenarios. So there is something to it, but there's still a gap. The gap seems shrinking, but there's still some fundamental differences. And I think it would be nice, just because most of the theory that I'm aware of on transformers tends to rely on linear attention, because that's when you can start doing theory, would be nice to really understand if there is a fundamental gap in expressivity, or like you have all of these results that are bringing this model closer and closer in performance. So are they sort of in the same reachable set, or are they not? And I believe in the end there will be not. There will be like some drastic difference, but I feel like we're missing that. I think that will be a good question. Okay, so just going to jump directly to results. So why does it all matter? So assuming we believe ICL behaves like some kind of optimization, it does end up having a different inductive bias. And there's this previous work from, I mean, the bottom archive papers are previous works looking at this, but this is mostly based on Andrew and Stephanie and Arslan work, where they noticed that like reasoning is a hard word. Like solving certain tasks by using ICL versus by using fine tuning doesn't behave the same. So in particular, you have this kind of like reversal or syllogistic deductions. So what you can do is you basically take a big LLM and you're trying to see whether it can invert a relationship, right? If you say zebra are larger than goldfish, can they tell you that goldfish are smaller than zebra? And it turns out that if you have the first part, the zebra are larger than goldfish, in context with other examples as well, then you can do this very well. If you fine tune on a data set of this form and then you ask, it can't do it. So there is a gap where there is and the same way with this kind of syllogistic, and this is like, you know, people have built like special data sets. So like for this syllogistic deduction, you know, what Andrew did is created this data set of like faked up objects like DAX and GREPs and ZUBs and whatnot. So, you know, you create all of this kind of synthetic data that you know, or you think there shouldn't be any interference with the pre-training data. And then you tune on this and you kind of just see this very clear effect that, you know, if you have the information in context and it's processed in context, somehow you're able to do something that you can't do without it. So there's
Yeah, so there's a comment about like in this part, right? So I was gonna exactly ask like, well, why does it matter, right? So I mean, like as in like so you're characterizing, in context learning kind of behaves like you know, optimization.
Yeah.
And then I feel like that should tell me that we can use this analogy to characterize limits in context learning as contrast to fine tuning or other type of things, right? So I feel like isn't the thing to characterize like it, you know, what exactly is the behavior on a specific task, right? So for example, if you have like in context learning behaving like KNN versus linear regression, what does that imply for this task, right? I feel like there's still
I totally agree. I mean, we did not get that far. I think the community is more about making this kind of observations, and going to be a few more.
Which is very cool.
It's cool on its own, but yeah, it's missing the reason of why. I was going for, I think it's the kind of representations that you build when you have the information in context versus when it's stored in the weights. I believe that like when you do fine tuning, all the facts need to be stored in the weights of the MLP blocks. And because of that, the kind of the way they represent it is in a way that it can't do this kind of operations, while the representation that's built on the fly by the ICL, but that's a vague statement as well. So it needs to be, but it needs to be digged into. I also wanted, and I had a discussion with this, I also have a hunch that the softmax plays a crucial role. So a big question for me that I have yet not seen anyone trying is what happens if you do things in context, but you use linear attention? And it might be that it behaves a lot more like fine-tuning, and that would be quite telling if it turns out to be true. But I don't have data for that. What we did do, or what Andrew and Stephanie and the others did in this work, is they showed that if you augment the fine-tuning, so basically, okay, so the way the augmentation works is you take the pre-trained model, you give this information in context, and you ask the model to generate more data that shows the reversal. So basically, you're not introducing new information. You're just kind of pre-processing your data set using the LLM, but you're pre-processing your data set, so you're not introducing anything. And then you fine-tune the same LLM on the data that you've generated, you suddenly can solve this task. So what this is that ICL is more efficient at extracting information from the data it has than fine-tuning. So fine-tuning kind of fails. The information is there, is in the training set, and the transformer can use it, but fine-tuning fails to extract that information, while ICL is somehow more efficient at extracting the information because this augmentation helps you quite drastically. Actually, it does better than ICL if you do it this way.
That's super interesting. So it's somehow like if you're using weights for fine-tuning to extract that information in the set of examples, like maybe there's something with optimization that's hard to.
It could be. I mean, yeah. Yeah. Yes.
Just a quick hypothesis, and
Yeah.
super interesting. Could it also be related to that you might actually forget information during fine-tuning that's relevant?
Yeah.
Just to solve another kind of task, and then it's difficult to retrieve it later, while if you kind of add it in the data, you can focus on, you don't necessarily need to forget something in order to present this kind of.
That's a really cool hypothesis. So I'm going to try to get back to it. So I just wanted to say that there is some other paper from other folks, so it's not just our paper. So this is actually even more interesting. It's not presented as, it's presented as a data set. So this paper is just a data set paper. But what they do is they show that, like in Wikipedia, you have articles. So somehow I ended up with German and Spanish. I don't speak either, so it's going to be really hard for me. But there are articles that are just in German, and then there are things that are just in Spanish. And it turns out that if the model, this is a multilingual big model, has been trained on all of this data, if you ask, say, in Spanish about an article that was in German, the system cannot extract that information. While if you ask in Spanish, it can extract it. So somehow it can't bridge that world, or at least not very well. So here, in this confusion matrix, it says, okay, if I'm asking in the same language that the article is, and I know there's no article of the same article in the other language, I get good performance. Depending on the difference between languages, it really breaks. But, and again, it's not framed in a way that we're used to, but this cross-lingual open book is basically you give the article in Spanish and you ask the question in German, and then it can do it 96%. If the article is still in Spanish, but it's in context, versus it was trained on that article and you just ask in German. So it's again the same, like inability to use information it somehow has stored. Which is kind of similar to the other. And I was trying to argue that this is all about representation. So I'm kind of running out of time. So I'm just going to jump to a last slide because it connects a little bit to what you asked, which is we looked at in a physics of LLM kind of stuff. So we did notice that it's kind of quite interesting. So because factoids are stored in these MLP blocks, when you try to fine tune on new facts, forgetting kicks in quite quickly. And these plots are a bit messy to read, but basically it turns out that you cannot learn new facts unless you forget some of them. And actually you have this, if you do this with replay, which is what people might do, you have this kind of interesting behavior. Maybe it's not that interesting, but I'll mention it anyway, which is you first need to forget and then recover all the information. So basically what happens is that MLPs need to change how they represent stuff in order to store new things. And they can't just learn new facts while not touching the old ones. The only way it seems that we managed to do this with replay was to first have this dip where you first forget and then you recover and you know all of the things. But which is kind of interesting because in continual learning, we always try to just keep that information as it is and say we can add more information to it. But it seems that the way things are encoded in this MLP, because these are exact information, this is, so like memorization is different from learning, I don't know, MNIST or CFAR. And it might be that the dynamics of learning are quite different. It could just really turn out that the function is way more nonlinear. And that's why WC is not sufficient and so forth, because you really just need to memorize or you need to store exact facts. But it has this weird behavior that you can't learn new things without forgetting, at least in our experiments. It seemed like you always had to pay a cost, and then you can recover from that. So So I don't know what implication that has, but it's kind of interesting. And to the point you're making, yeah, like it could be that there is some forgetting going on that is affecting all of this. So I think it's a very interesting angle to explore. And with that, I think I'm out of time, so I'm going to just stop here. But yeah, questions.
I think we're out of time, so maybe you can ask in the coffee break. But let's thank the speaker.
Thanks.
All right, hi everyone. So I actually just noticed that I've got the wrong event on my title slide, because I gave a similar version of this talk at the Bayesian on Parametrics conference. I can't tell if it's 2 days ago because of the time difference, or 1 day ago or something like that, but very recently. But I'm really excited to tell you about this work, because I think it's an example of some lessons that I think we can learn from Bayesian learning, and in particular Bayesian non-parametric learning. And I want to sort of speculate on how that might actually help in training large neural networks, and how maybe ideas from Bayesian non-parametrics can be useful in coming up with new learning algorithms in large neural networks. So to start with, I just wanted to tell you that this work was done in collaboration with people from Imperial College London. So there's Guillaume, who's the first author in one of the papers that I'm going to talk about, and she's currently interning here with MT as well. So it's nice to see her on the other side of the world from where we usually meet. And then similarly, Tycho van der Oudera, who's a PhD student with me, still at Imperial College London. He also was instrumental in coming up with the ideas for this work. And then I also want to thank Professor Sarah Filippi, who is Guillaume's co-supervisor, and together we've been working on trying to get these ideas working. So the story I'm going to tell you is based on a few papers where we discuss these ideas. So one was or will be published in ICML in 2 weeks' time or so. So this is about adjusting model size in continual learning. And we'll also have a paper that will roughly follow the argument in this talk, which will soon be on archive. So if you're interested to learn more, keep an eye out on that title, and it'll pop up on the archive soon. Okay, so what is the main point of this talk? The main point that I want to get across is that I think that ideas from Bayesian non-parametrics may actually help to create training algorithms that have new capabilities that can help deep learning. And in particular, what I want to drill down in this talk, what I want to drill down on in this talk, is how big should a model be? So how many neurons do we actually need in a model to learn everything that there is to learn about the training data? So why is this a relevant question? So I first want to justify this a bit. So the first reason why this is a relevant question is because the neural network size determines the compute and energy costs. And we know that it's possible to shrink a model after training. And people often do this in order to reduce deployment costs. But the current advice when training a model is to actually make your model as large as possible. And this somehow presents a bit of this somehow gives us evidence that this must be inefficient, because we know that at the start of the training, we need the model to be really large. And at the end of the training, we can compress it. But somehow in between, we need to keep all those neurons around to actually do some kind of learning. And I somehow wonder, can we not come up with a learning procedure that finds the size and the weights of the network in a unified way, and maybe grow and shrink the neural network as is required by the current data set to avoid unnecessary computation, right? So we might have to start with a small network and then grow it really large, but then maybe halfway through training, we realize that actually we can whittle down the size of the neural network without losing anything. So the second reason why I'm interested in this question is because data can actually arrive in a streaming fashion, right? So LLMs are trained on basically one pass through a large data set, but every single day you've got new information arriving on the internet. So ideally you want to train it in a kind of streaming way when you get more data arriving. And that basically means that a priori, we don't know how large a data set we have. So that also makes it difficult to determine how large the neural network should be, even using these scaling rules, because they require you to know how much data you actually have to train on. So yeah, the second sort of question that I want to discuss is, can we maybe grow a neural network size as we see more data to avoid poor performance that you would get from having a constant size, right? So hopefully you would agree with me that if you have a neural network of constant size, if you constantly feed more data through there, eventually you'll run out of capacity. And I mean, that also fits with the observations that are currently used in training models, that if you've got larger data sets, then you should use a larger model. Okay, so the goal that I want to look at in this talk is the goal that I'm researching and I'm trying to get to is that we want to minimize the model size at every single point in time during training, while maintaining near optimal performance at the end of training. And this sort of fits with the goals of large-scale machine learning at the moment, where getting every last bit of performance is very valuable. So people are really quite willing to pay any price as long as you get some kind of performance improvement. And then a secondary goal is somehow to, not waste any money, right? So secondarily to getting the best possible performance, you want to minimize the model size. So this is sort of like a constrained optimization problem, where the constraint is that you want to not lose any predicted performance, but otherwise you want to minimize model size. You had a question?
Yeah, I have a question about this goal, right? So as in I assume when you say maintain near optimal predictions or near optimal performance on task, so that is the training task, right? So but we just heard, had this whole discussion about usually when we train models, we actually have several tasks in mind, right? So, so we actually want to do a little bit better than just the specific task that's represented by the training task. So, and I'm just curious as to if we just kind of put constraints on the model during training, how does that affect the representations that we're learning?
Yeah, okay, so basically I will only be talking about single layer models from now on. So I'm a long way off from actually doing this in practical deep learning. But I mean, the goal is that you don't want to sacrifice any performance. And then your question is, well, is it performance on one particular task or is it performance on all these particular tasks? I would say, in the broadest way possible, that's the goal. But yeah, how to get there, this goal is quite far away from what we can do now. Yeah, okay. But I think we agree on what the ultimate goal is. Okay, so let's just remind ourselves. Okay, so to start addressing this problem, I want to abstract and simplify the problem as much as possible, and then come up with a really clean solution in a very simplified problem. And then hopefully we can then grow this again, these solutions again to cases that are practical in these large learning, in these large models that we learn with. But if we simplify the problem of all machine learning, I sort of do believe that what we actually do when we train models is mostly just curve fitting. And that helps us to come up with a simplification of the problem, because ultimately the thing that all of machine learning, most machine learning, definitely large language model boils down to is that you've got a set of inputs and then you've got a set of outputs that you want to predict. And ideally you'd make good predictions at points that are not exactly at your training points, so that you generalize. And your goal is to figure out how to make a prediction at any input point from some data set that you have. Hopefully you would agree with me. Okay, so first I want to sort of recap how we would solve this problem with a neural network, and then I'm going to simplify down, and then at the end of the talk we can speculate on how the simplified results might apply in the large neural network case. But when solving such a curve-fitting problem with a neural network, the first thing that you have to do is you have to design your inductive bias, right? So this is determined by your connectivity structure between all your neurons, right? So the most famous example of connectivity structure determining inductive bias is the difference between a fully connected and a convolutional neural network. But we still have to design neural network architectures these days, and that still determines the inductive bias. And that's still something that has to be done manually by humans, right? So that's the first choice you have to make. the second choice that you have to make is that once you've got this connectivity structure, you need to decide, well, how many neurons do you add in each layer? So do you make them really wide or do you make them small? And that determines the cost, but also the degree to which it can fit the training data. And then finally, you've got this method that is actually automatic. You want to find the weights, and there you just feed your data through your network and you run back propagation. So currently in machine learning, this is automatic, whereas these two steps, choosing network size and connectivity structure, that requires a lot of human thought, right? So people think about scaling laws to determine network size. That requires a lot of reasoning. People think about how to design architectures, and that's a global research effort with lots of research groups all over the world trying different things and seeing what works. So if I would be uncharitable, I would say that there's a lot of trial and error in these two parts of the neural network design process. But of course, there's a lot of mathematics behind this as well, but at least it takes human effort. Another point that I'm trying to make in this talk is that I think that we should try and find a unified learning procedure that solves all these three different problems at the same time. That these problems should be tackled together and that they also influence each other. So the reason why I'm talking about architecture now is because you can't talk about how big your neural network should be independent of the question of what architecture you use. So for example, on image data sets, we know that in order to get even just to fit the data equally well with a fully connected neural network, you need a much larger network than if you use a convolutional neural network. So if you want to come up with an automatic procedure for determining neural network size, you also need to come up with an automatic procedure that at least is aware of the inductive bias and of the connectivity structure. Okay, so let's formulate the problem which we can actually solve, because in the spirit of let's walk before we can run. So I've been talking about deep neural networks, and that is the ultimate goal. But for now, let's just try and answer the question of how do we do this in a single layer neural network? Because even in a single layer neural network, coming up with a unified training procedure that solves all those three examples, I think that's an open problem. So let's simplify this again. And in that case, the function that we're actually trying to learn is going to be parameterized in this way. It's just a single layer neural network. You've got your nonlinearity, and in order to calculate your resulting nonlinearity, you pass in the input through something that depends on some weights, and then you might have some global parameters for your nonlinearity. And then once you've calculated your first layer of your neural network, you then multiply each neuron by a particular weight, and then you sum it up, and then you get your ultimate function. So single layer neural network, you could also call it a basis function model. And in this formalization, the goal is to find the hyperparameters, the inductive bias, right? So this might determine the connectivity structure in this basis function, and that's global to the entire network. So that's why we have one global theta. We also want to determine the size of the model, so the number of neurons that we add. And we also want to determine the weights. So that's the weights that we feed, the basis function depends on, and the weights of our final layer. And hopefully you see the analogy to how this actually fits with even in deep cases. So the hyperparameters control the inductive bias, the size controls the cost, and then the weights actually control the function. So let's start by finding a clear answer to this question for single layer neural networks. Okay, so to start with, I just want to recap why deep learning currently doesn't have a particularly satisfying solution to this problem. Because deep learning basically says, well, you've got your training loss, let's just minimize the training loss. So let's see what happens if we try to answer these questions with the minimizing losses paradigm. So what we can do is we can initialize our neural network. So in this particular case, I'm using an activation function that is a bit of a local activation function. It's like little Gaussian bump like that, and then I sum them all together. And then at initialization, I've got a function that looks roughly like this. And then what current neural networks do is that they take a fixed a fixed inductive bias and a fixed model size, and then do gradient descent on the weights only. So the inductive bias in this case would be determined by the width of the nonlinearity. And if we make the width of that nonlinearity narrower, then our function can be wigglier and it can fit data easier. And if we make the width of that nonlinearity wider, then the functions will be smoother and it might be harder to fit the training data. So let's run, yes, question?
Clarification question. So you're not considering kind of like, that's not the topology of the network though.
Well, so no, it's not the topology of the neural network in this idea, but we do have one parameter that controls the inductive bias. And the analogy is that the topology of the neural network also controls inductive bias.
I agree.
Now, yeah, sorry. Sorry?
Like choosing the activation function,
Mm-hmm.
the hyperparameters, is a bit different than the inductive bias that comes from CNNs and RNNs.
Well, it's a different source, but it's both inductive bias.
No, I totally agree. I'm just wondering, like intuitively, do I expect, knowledge here to transfer, right?
So I think yes. And one reason why I think yes is because another part of my work, we actually do have an automatic procedure for determining whether a layer should be convolutional or fully connected, or even what kind of convolutional. And I've got some references at the end about that. But so we've applied the same principle to actual architecture learning in deep neural networks, and it actually works. The spoiler is that we get ResNet style architectures popping out. And that's about as much as we can do at the moment. But so I would really argue that this simplification does generalize, because the method that we will use to solve this problem in this 1D regression setting actually works in that architecture case as well. But I'm getting ahead of myself. Okay, so so if we train the weights with W and then animate that, we get something that looks like this, right? So we start at our initialization, and then we get something that eventually fits the training data. Now, what will happen if we then also try to fit the hyperparameter that controls our inductive bias and the size of the model using this same criterion of trying to minimize loss? Well, this might not be a surprise, but I think it's helpful just to remind ourselves that this can happen. If you did this and trained all this stuff together, you'd overfit, right? And the reason for that is that making your model smaller or using an inductive bias will never help you to fit your training data, right? So making your model smaller only constrains what you can fit, and inductive biases are also a constraint on what you can fit, right? Usually inductive biases shouldn't really constrain how well you actually fit your data, but it's never going to make your model more flexible. Yes, question.
Is this true if you just optimize M, like not theta? Because I believe theta is what makes this overfitting happen.
Yeah.
But if you keep theta fixed and you just optimize over M.
So yes, well, okay, so at the very least, making M smaller will never improve your objective function.
Sure, but
right? So there's no
M will go to infinity, right?
Yeah, exactly. Yeah. So we've got two problems here. We've got the problem where M is encouraged to become larger, and that's not what we want. And arguably. So basically, yes. Okay, great point. Do we want M to go to infinity? And the answer to that is yes and no. But at least we agree that it would be encouraged to go to infinity. And then you've got this second problem that if you've got a huge model with lots of parameters, then then you start optimizing your inductive bias, and you're also encouraged to make it as flexible as possible, and then you overfit. Was there another question? No. Okay, but this is what happens.
Increase the data size.
Sorry?
Increase the data size.
Yes, but then so then the question becomes, how quickly do you increase the data set size relatively? Oh yeah, well, but I mean, this is a genuine question. You can think about this. Yeah. Okay, so restricting model size never improves loss. So you're encouraged to add more add more parameters. And you get overfitting. Okay, so basically, I think that Bayesian model selection is a super powerful capability of Bayesian inference that's really underappreciated I would say in deep learning, but also Bayesian deep learning. Right, so everybody has probably heard about Bayesian deep learning, and the usual story is, oh, we want uncertainty. And I think it's maybe fair to say that uncertainty, when is it actually useful? Well, sometimes it can be useful, but people are doing pretty well without uncertainty. But Bayesian model selection is a procedure that is prescribed by Bayesian inference that tells you how to solve this problem of choosing your inductive bias. And I think that's super exciting, because then hopefully that can be a principle that tells us how we should design architectures and replace the human design. And that's what I was talking about earlier. So the work that we had on automatically selecting architectures, that's based on Bayesian model selection. Okay, so let's try and answer this first part of our problem, right? So remember, we had 3 parameters that we wanted to estimate. We had the weights, the size, and then the inductive bias. Let's see what the Bayesian answer is to selecting the inductive bias. So let's just accept for now that we use this, let's just accept that we're going to use really large models, and let's just say that we've got an infinite number of parameters, because that's what people both recommend from double descent, and that's what we got from our minimizing training loss. And let's see whether Bayesian model selection can solve the overfitting problem. And one reason why you might do this is because Bayesian inference is rumored to be robust to overfitting. Okay, so the nice thing about Bayesian inference is that it's a prescriptive procedure that tells you what you should compute in order to solve particular problems. And the only thing that you ever need to compute is your posterior on all your unknowns. And then what's cool is that you get really nice behavior that comes from it if you do it correctly. So let's just apply this in this particular case. So like I said, if you just do Bayes on all your unknowns and you just do the weights, then you get a little bit of uncertainty. But what we're looking for is this benefit number 2, which is that if you do Bayesian inference on all of your unknowns, and now they're the weight and the hyperparameter, then Bayesian inference essentially tells you that you should compute a normal posterior on your weights, and then a second posterior on your hyperparameters, which uses this quantity here called the marginal likelihood as its likelihood. Yes, question?
So if you put a prior on the weights, getting the posterior is obviously very hard. And now I have to marginalize out the very hard posterior.
Well, we don't have to so this is an interesting point. So if you solve the problem for finding a posterior over the weights, you get this marginal likelihood quantity for free.
Oh, sure. Okay, I see what you're saying.
Right. So in practice, what I'm saying is that doing posteriors over both quantities is really hard. But what we should be doing, what's maybe the relatively low-hanging fruit is that if we're Bayesian deep learners and we're trying to find posteriors over weights, then most approximate inference methods, and I would even say all, imply a particular approximation to the marginal likelihood, and then just find a point estimate over your marginal likelihood, and then you already get some adaptation over inductive bias. And this is the procedure that's a slight simplification of what Bayesian inference tells you to do, but this is the procedure that I'm going to show, and this is the procedure that I'm advocating for, because I think it's the right balance of complexity to
It's interesting because this is doing Bayesian model selection on an approximation, right? So it's not the true posterior, the true kind of margin.
What I'm saying is that if you do approximate Bayesian inference, you get an approximation to both your weight posterior and your marginal likelihood.
I think that's really lovely, right? You get that for free. Yeah. Right? So I'm just wondering, does the sort of theoretical guarantees of Bayesian model selection work when everything is approximate?
No. Right. But I mean, that's I think asking for theoretical guarantees when coming up with a method, when has machine learning ever really cared about that, right?
I thought you care about it.
Huh?
No?
I mean, I do care about it. I'm being a bit facetious here, but I mean, I really don't think that we should be I mean, there are lots of theoretical arguments. Like MT says, I do care about this and I do work on this, but let's not stop that from, yeah.
Exactly. I'm not trying to let enemy get perfectly the enemy is good.
Yeah.
I'm just wondering, it's not an adversarial question. I'm just wondering kind of like the exploration of what is lost through that approach.
Yeah, so that's something that I'd love to talk about afterwards. Yeah, exactly. I do worry about this. Yeah.
Just a question, is this Bayesian neural network?
Yeah, so what I'm already starting to say here is that we should be looking at Bayes to solve all these three problems. And in order to solve this, so you can also see it in another way, in order to solve this problem of what should your inductive bias be with Bayes, then you get uncertainty for free. Just depends on what way you want to look at it. There was another question?
Sorry, I think I can also ask that later, because I was a bit surprised that you make this overparametrization assumption when you're Bayesian, because I was hoping that you don't have to if you go Bayesian, because if you take now an average over the posterior, I hope that would give you so much smoothing that you don't need to be overparametrized or that much overparametrized anymore.
I'll be talking about that. So overparameterization is something that I'll be talking about. Yeah, exactly. That's where the non-parametric thing comes from. Yeah. Okay. So let's see what happens if we apply this Bayesian answer to our little toy model. So here I've initialized my now Bayesian procedure at the solution that I got from the overfitting procedure that we got just from using the training loss. And so it overfits terribly, but now we've at least got some uncertainty. It's another little funny observation that, is this overfitting? I would say maybe it's underfitting because it's actually super uncertain everywhere. So, you know, as a little joke, I often think that Bayes never overfits, it only underfits, but in different ways. Anyway, if we then start the learning procedure, then what happens is the following. Whoop, look at that. It goes from the overfitting solution, and then it ends up preferring a solution which hopefully you would agree looks a lot better. And here I've plotted the training loss. So this is now the marginal likelihood as the objective function, rather than the fit on the training data. And what's interesting is that you actually see that in this example, the fit becomes marginally worse, even though the generalization becomes better. So it actually decides to not interpolate the training data perfectly. It marginally interpolates it slightly less well, but you get a huge benefit in this marginal likelihood training objective. So that's what I'm advocating for, that we should be using the marginal likelihood to find these inductive biases rather than just the training loss. Now, one question that I sometimes get at this point in the talk is, why does the marginal likelihood prefer the method that generalize, or the model that generalizes better? What is it about the marginal likelihood that makes it a better training objective? I can talk about that afterwards if you're interested. But hopefully you would agree with me that if we follow what Bayes does, it gives a more desirable outcome. Another question.
Yeah, sorry, just because you brought up this question, it's like, how can you even talk about generalization at this point? I mean, do you make an assumption about the data generating process?
Yeah, so I've got a test set that I sampled these training examples from that test from some generated. I sampled everything uniformly, yeah, and if I would have drawn the test data there, you'd have seen that it would have generalized better. Yeah.
Does it fit to the prior then that you're assuming here?
I can't remember how I generated this. Well, actually, sort of yes and no. But you're right that your prior, like if you choose a really bad prior, then the method won't work. Yeah, sure. But ultimately, the only prior that we chose here was the prior that was implied by L2 regularization. So, did I cheat here? I would argue no. I'm just doing roughly the same as what deep learning would have done. Yeah.
Is it?
Huh?
Is it?
I think so. Yeah. L2 regularization. Deep learning does L2 regularization. It's just that we interpret that as a density. Sorry.
I don't think so. No. Deep learning people don't use regularization.
Well, so you were saying earlier, yeah, I mean, this is, some people do, yeah.
L2 is widely used, but I think what matters more, it's the implicit regularization, which is like an L2 on the norm of the gradients, which is, I don't know exactly what that means, but usually that's what we regularize, the norm of the gradients.
The point I was more trying to make here is that I don't think I was cheating with matching the prior to the data set here. Okay. So where did we get to at this point? Well, where we got to is we had this model where we used a large number of basis functions, and we performed Bayesian inference over the weights. And from Bayesian inference over the weights, we got this marginal likelihood, which we used as an objective function for learning the inductive bias. We call that type 2 maximum likelihood. And then we got this better generalizing solution. And the way that I actually did this, you may have noticed that a neural network with an infinite number of basis functions is actually a Gaussian process. So I didn't actually train an infinite number of numbers. I did a Gaussian process representation of this, and that's equivalent. It's a one-to-one mapping between the two. But interestingly, the predictor is still in the form that we wanted all the way at the start of the talk. Right? So I said all the way at the start of the talk, I wanted to solve this problem of how big the model should be and what the inductive bias should be with predictors that were single-layer neural networks. But predictors from Gaussian processes are single-layer neural networks. So I can, so if you know Gaussian processes, you might recognize these equations here. So it's just that the basis functions, the nonlinearities are prescribed by the kernel, and the weights you can compute in some kind of closed form. But ultimately, it is represented in a way of this single-layer neural network. Was there a question?
Yeah, so it's a bit of a high-level question, and maybe like you're not addressing it because you're looking at a single-layer model. But if you have symmetries in your parameterization, so you have different thetas give you the same function, I don't see how this machinery reflects that, and whether it has an opinion between all of those choices. Because the likelihood is just looking at the functional behavior, and it kind of ignores the fact that, or maybe I'm wrong.
Yeah.
Sorry, can you? Yeah.
So if you have symmetries in your parameterization, so you have,
which you don't in this particular case, indeed, because it's a single layer model, yeah.
In a deep neural network,
yeah.
Like, how is that reflected in that formalism? Like, how does this, like, does the marginal likelihood have a preference between all of those thetas that give you the same function?
Yeah, this is a really good question, and I think there are. So there are two answers I can give to that. Firstly, there's a practical work that we've done on Bayesian model selection in deep neural networks. And the short answer there is it roughly still works. And what's interesting about Bayesian inference is that if you do a few popular approximations to make it work, then Bayesian inference prescribes that you look for wide minima. So in that sense, that's completely consistent with what the deep learners are doing. But if you want to do Bayesian model selection in this way, then there are a few subtle changes that Bayesian inference tells you to do that the deep learners haven't figured out yet, or don't do in practice. But again, I can talk about that later. Yes, and then there are lots of theoretical arguments as to why parameterization doesn't matter in principle for Bayesian inference. Bayesian inference is parameterization independent, but when you do approximate Bayesian inference, then these symmetries do become a real pain. And yeah, we had another paper on that, which I can also link to. But this, yeah, so long story short, these symmetries in the parameter space, it seems like you can make things work, but they're also still an open problem. Yeah. Okay, but that's where we are, right? So where we are is that in the single layer case, we've now got a principle for finding the weights, and we've got a principle for finding the inductive bias. So we've only got the third problem still left, which is how big should the model actually be? Now, in this Gaussian process interpretation of things, we do get an answer for this, right? So Gaussian process basically prescribes that you use one basis function per data point. So in some ways, we actually do get an answer. We get an answer that says, well, just grow your neural network linearly with the number of data points. Now, this is a real pain. This makes your networks far too big. And it means that you need to memorize your training data. So there's no compression going on if you just blindly listen to what the Gaussian process formalism tells you to do. And that's why I think that there's still a problem here, which we'll talk about next. But question?
Yeah, sorry, because
So, but aren't you then kind of in the same kind of, aren't you then operating at the interpolation threshold exactly? So isn't then your optimization problem really badly conditioned, or don't you care so much because it's just...
Okay, so this is where I think people from Bayesian non-parametrics were totally not surprised by this whole double descent thing, because in Bayesian non-parametrics, you were defining models with an infinite number of basis functions and then learning with that. People have been doing that for decades. So to answer your question specifically, the model of a Gaussian process is specified with an infinite number of basis functions, but the solution is representable using one using one basis function per data point. And this is one reason why you don't have these weird bad behavior from double descent in Bayesian non-parametric models, because ultimately you're always operating in the overparameterized regime. And this is part of what I want to, this is one of the themes in this talk, which is also in that paper that we're going to put on archive soon. Another question.
Sorry, real quick clarification. So your P of D is going to depend on your P of W, your choice of prior, right?
Yes, your marginal likelihood is going to depend. Well, and what you're actually doing is you're learning what your prior over your weights or over your function should be by doing type 2 maximum likelihood using the marginal likelihood. Yeah.
Yeah, so I'm imagining kind of like your choices of the, like, so let's say you choose your P of...
Can we talk about this afterwards? Yeah, this is an important thing, but it's, but not for the current narrative. Okay, so where are we in our goals? Well, we've got a good solution for finding the hyperparameters. I've shown you that it gives you good behavior. A good solution for finding the weights. And now what about the size of the model? Well, we've got this weird answer that we need to memorize everything, and that's sort of not what we want. We want something smaller. Right, but at least what we're told is that as we get more data, we need to grow our model, and that's at least fits with that intuition that we had about continual learning at the start. Okay, so what I think the Bayesian answer to model size is, and I think that Bayes actually prescribes that we should be using an infinite number of basis functions, which is what Bayesian non-parametrics is all about. Okay, so we basically stumbled so far into using large models because we said, well, we want to at least fit the training data. And we've got all these arguments about double descent, that we should use overparameterized models. But what are the classic arguments for using non-parametric models from the statistics community? Well, one is that using these super large overparameterized models allows for consistency as the amount of data grows to infinity. So if you've only got a finite number of parameters, then you know that there are certain functions that you simply won't be able to learn, and that means that you'll lose out on predictive accuracy as you get lots of data. The second classical reason for infinite basis functions for non-parametric models is that they're needed to quantify uncertainty well, because you can only ever quantify uncertainty when you have a basis function to be uncertain about, right? So without having a basis function here, the model would just be very certain that you need to make a zero prediction. And then I also think that continual learning requires parameters and basis functions everywhere, because if you suddenly get data in a new region where you don't have any free parameters anymore, you won't be able to learn it. Right? So what we want is we basically want to place basis functions everywhere in the space so that we always have some model capacity to learn from data with. Okay, so those are the classical arguments about Bayesian non-parametrics. And that leads you in the single layer to using a Gaussian process. But then I want to return to this question: can we find a compressed model representation? Can we find a model smaller than n basis functions? And so right now I just want to hypothesize, well, maybe we can use Bayesian inference to also find the model size rather than just the inductive bias. Because that was the promise that I mentioned earlier. Why did we use Bayes to find the inductive bias? Well, because Bayes says all your unknowns, just find a posterior over it. And so what we can try to do now is, instead of just finding a posterior over the weights and the inductive bias, which worked so well so far, we now also try to find a posterior over the model size. And then we might do a type 2 maximum likelihood over both the inductive bias and the model size. Now, I think that this is a bad idea. Yeah.
Small question. Z, is it in theta or W?
In W. Yeah, so those are the weights that you pass into your, that's the first layer weights, let's say.
There's WM and then there's ZM, and both of them are in W.
Yeah, exactly. So you've got the weights on the input to hidden layer neural network part, and then the hidden layer to predictor part, right? Yeah. Okay, so this is one thing that you could do, but I think that this is a bad idea. So why do I think that Bayesian model selection over model size is bad? Well, firstly, what we would do if we would follow this procedure is we would say, what size of a finite model should we be using? But if you use a finite model, then you lose all the nice properties that make non-parametric models good for these three reasons. So that's one reason why I think we shouldn't be doing Bayesian inference over the model size. And the second really big reason is that if you actually set up your model correctly, in order to make sure that it has good scaling behavior, i.e. that if you add more and more parameters, then the model stays sensible, then Bayes doesn't even distinguish between models of different sizes. So it won't even give you the answer that you want. And this was discussed in one of my favorite papers ever, which is called Occam's Razor. It was by Kåre Rasmussen and Zubin Garamani. They had this plot in their paper, where they had a little regression example with some data, and then they added more and more basis functions, and they did it in such a way that the model had good scaling behavior, which meant that as you added more basis functions, you would end up converging to a model with good predictive properties. And what they showed is that the marginal likelihood stopped preferring small models. It would basically say, well, you know, as long as your model was bigger than order 5, I don't care how big the model was. And if anything, if you look at this as a posterior, it places all the mass of model size at models that grow towards infinity. So this is a reason why doing Bayesian inference over model size doesn't even work. Yes?
Isn't it just that they chose a bad prior on the model size, actually?
No, well...
if you penalize larger models, then it will start.
Yes, but then the penalization... So your question is, could they not just put a prior on model size? But then that brings you into all kinds of philosophical strange things, right? Because that basically means that a priori, you're telling the model how many basis functions it should be using, right? So it's only the prior that would determine the size of the model if you have a marginal likelihood that looks like that.
If you just say that actually you're decreasing, you don't have to say how many, you just... Sorry. If you take any prior that is decreasing the model size, it will just give more mass to the smallest model that has this kind of...
Agreed, that's what Bayesian inference would do, but I'm arguing that this is a bad thing to do, because then the only thing that would be determining your model size is the prior itself, right? So with a marginal likelihood like this, if you have a decreasing prior, then it's only what you put in the prior that determines the model size. And you still, for the first reason that I mentioned, lose the good properties of non-parametric models of having basis functions everywhere, which allow you to do continual learning and allow you to do uncertainty estimation.
We can discuss that later. I'm not completely convinced by this, because all these models are equivalent, actually, in the sense that they find a solution that is very similar.
Yeah,
and
agreed.
The fact that we want a smaller one is actually indeed a kind of subjectivity, but this is where you want to be Bayesian.
Well, I guess what I'm saying is, I think that there's another solution to this, and I think there's a better solution to this than to try and do inference over this. Yeah. So I guess what I'm saying is that if you believe this picture, I think that the data is telling you that you want a model of unbounded size, an infinitely large model, which also fits with double descent and all this kind of stuff, right? Okay. So yes. So I'm arguing that Bayesian inference over model size is the wrong principle to select model size. So what should be the principle for selecting model size? So what principle can determine a compressed model size without removing the benefits of these non-parametric models? So we want to have our cake and eat it. We want both nice properties. We want both the properties of overparameterized models, and we want to have a compressed representation. So I think that the solution is to define a model which has an infinite number of basis functions. Let's just use a non-parametric model. And then essentially say, with variational inference, what is the closest model with a finite number of basis functions that approximates this non-parametric prior that we defined arbitrarily well. And it turns out you can do this, right? You can actually, for any finite observed data set size, there is an arbitrarily good approximation to the non-parametric model that only uses a small finite model size. Yes, question?
Very quick one. Sorry. But that wasn't it just imply that on the side of the Occam's razor example that you would just pick 5?
No, because it's very different to define an infinite a model with an infinite number of basis functions and then approximate it versus defining a finite model which wouldn't have all these nice benefits of non-parametric models and then use that.
But is it the same class of basis functions?
Well, the predictor that you will get will be the same class of a predictor. They'll both be single layer neural networks. But the way that you choose the number of basis functions and the way that you choose where to place the basis functions and all that kind of stuff is different.
But didn't this plot, the Occam's razor plot, indicate that if you take now the best model that picks 4, for instance, basis functions?
Why is that the best model?
Sorry, I thought, because to me it looks like starting from 5 it works nice.
Yeah, exactly. Starting for 5 it works nice, but there's no difference in the predictions between all of these, and the marginal likelihood doesn't say that any one of these is the best one. There is no best model here, is the point.
That's true, but you could say like 5 is sufficient, and 4 isn't working as good. So the best of those 4 basis functions won't approximate it as well. If my approximation here should be smaller, if the epsilon should be smaller, then...
Yeah, but if you choose a finite model, you would lose these 3 benefits, right? You would lose the good uncertainty bands, right?
So you're looking now for a finite model that serves multiple objectives. That also is...
Yeah, so we want to have our cake and eat it, right? We want all of these nice properties from Bayesian non-parametric models, so having basis functions everywhere, so that we can do continual learning and that we've got good uncertainty and that we can get consistency. But we want to approximate it using only a small number of basis functions. And that's very different from starting with a model that only has a finite number of basis functions. Because if you start with a model with only a finite number of basis functions, like here, then you'd have bad predictive uncertainties out here. You'd be really overconfident. There wouldn't be any basis functions out here, so you wouldn't notice that you're not fitting well if you see data there, and you wouldn't have this consistency. Please, can I? Yeah, maybe at this point, I just want to finish telling you the procedure, because the procedure will be that you'll need to change the number of basis functions as you get more data in order to keep approximating this non-parametric model well. So the whole point is that you don't pick a model of fixed size. You don't infer a fixed size of the model, but the size needs to scale depending on the needs of the problem. So the procedure that we follow is that we say we've got our posterior over functions, and then we approximate it using a finite neural network. And I don't want to go through the details of derivation of all of this. I'm happy to do this on the blackboard afterwards if you're interested. But the interesting thing now is that you get an elbow, an evidence lower bound, which depends on the distribution on the weights. And the input weights, so these together are the capital W that we spoke about earlier. But it also depends on the data set size, and it also depends on the hyperparameters. And this elbow, if we optimize it with respect to all of these parameters, it becomes a unified training objective that tells you how to select all these parameters, right? So it tells you how to select the weights, the model size, and the inductor bias, and the theta. Yeah, and what we find is that if you use too few inducing points, then you get penalized for that. Sorry, inducing points are neurons. That's just the Gaussian process terminology. But if this M is too small, then this elbow will be telling you that you cannot approximate. It'll penalize you because it tells you that you're not able to approximate the non-parametric model with so few basis functions, and that will then encourage you to add more basis functions. And what actually happens is that you get a diminishing returns property. So if you look at m, the number of basis functions, and then you look at this elbow, then what you'll see is something like this, where after a particular point, the gap to your true model becomes arbitrarily small. And so we proved this a few years ago for these single layer models, that gap does become arbitrarily small. So I'm just trying to say that there is a small number of m that's smaller than n that allows you to get arbitrarily close to your target. Okay, so it's a unified objective function. So now I'm going to tell you the only new thing. I think I just need to finish it off, but I'd love to talk more later. So now this slide is the only new thing that we have in the two papers that I mentioned all the way at the start, which is how do you know when you've got enough inducing points, enough basis functions, right? Because one property of this elbow is that if you add more basis functions, you can always approximate your non-parametric model better. So you need a principle to determine when you can actually stop. And the principle that we use is that we basically also got an upper bound on the marginal likelihood, and that also converges to the right thing. So we basically say as long as this is smaller than some kind of epsilon, then we know that we've added enough basis functions to be very close to a true non-parametric solution. And there's some details about how you do that in a way that means that it's not a hyperparameter that's sensitive to tuning. And Guillaume has done a lot of work on coming up with that and also showing that it works, but I'll leave that as a detail for the paper. Yes, so we select M such that the upper minus lower is smaller than some tolerance, and that gives you a guarantee on how good your approximation is. And then together with David Burke, we actually proved that that in the regression setting, you can actually get an arbitrarily exact approximation with a small number of basis functions. Okay, so the point that I want to make, I don't want to go through all the maths. I'm happy to go through it afterwards. But the point that I want to make is that this simple rule, which we got from doing Bayesian inference, using a non-parametric model, and then approximating it, that we get a simple rule for determining the model size, the inductive bias, and the weights, and that we get really interesting adaptive behavior by training in this way. So here I've got a little example of continual learning, and this is in Guillaume's paper. And we've got three settings here, three different continual learning settings. One where the input range grows linearly with the data set size, so that's this one. What you'll see is that the range that we see data will continuously increase. One here where we see data sampled randomly on a fixed interval. So what's going to happen is we're going to see more and more dense data here. And one where we've got a lot of data in some kind of region, but then we get data that's occasionally sampled from a heavy tail distribution, so we get these outliers. And what you see is that from this training procedure, we see that the number of neurons that we use in the model, that the growth of the number of neurons depends on the amount of novelty that's in the data. So we get really interesting behavior coming out of this, right? So in this example where the input range grows, we see that the number of neurons grows linearly, and that's because there's a constant amount of novelty in every batch of data that we see, and we need a constant amount of neurons to be able to learn from that novelty. In this example where we only get data in a particular fixed region, the amount of novelty that we see in every single batch decreases every single time, and so the number of neurons that we select converges to a particular constant. And then in this case with outliers, most of the time we just get this convergent behavior like we get from this example where we get data in a particular region. But then occasionally we get some outliers, and then the model adapts and adds more parameters, and then it might converge again. So one example of what I think is pretty interesting behavior. Grokking. That's another interesting behavior. The number of neurons actually depends on the inductive bias. And our procedure automatically adapts to that. So let's take a look at this example here. So I've got the data set that I showed earlier, and I initialize it with one neuron and one basis function. And then the first thing that the method does when it tries to start learning on this data set is it adds more neurons because it needs capacity to actually see that entire training data set. And then the first thing it does to actually fit the data is it chooses an inductive bias that allows functions to be wigglier and wigglier. And then as it sees that as it fits the data better with this wigglier function, we see that the number of neurons is constantly increasing to adapt to that to the fact that the function can become wigglier. So it needs more neurons to actually fit the data. Now, what's interesting in this case is that if I keep training, I've also included in this analysis an inductive bias that will allow it to generalize much better outside the range of where we have data. And this inductive bias uses a particular underlying structure in this data. And I don't know, have you spotted it yet? Does anybody see a particular principle in that data set that allows it to generalize really far away from where it's seen training data on the real line? So this is an example of grokking in single layer models. So if I keep training, there's a secret inductive bias that I haven't told you about that is in the model, and that's periodicity. The marginal likelihood does actually recognize that there's periodicity there. And so we see something very similar to grokking, right? Where you go from a model that fits the training data, really well. It can't really fit the training data better. And then suddenly it notices this underlying pattern that allows it to generalize a lot better. And not only does it generalize a lot better, but our procedure for adapting the number of neurons suddenly can reduce the number of neurons as well. So I think that, grokking, so there's a lot of papers that explain grokking as finding a lower complexity solution to a particular data set. And in this single layer example, we can reproduce that. And we can also show that this reduction in complexity can translate to a reduction in computation that's needed as well, because the number of neurons that you need to represent this solution is a lot smaller as well. So that's another interesting behavior that you get from this very simple principle in training. And then here's another example where I initialize with a really wiggly function. And in this particular case, the first thing that the model does is memorize all the training data. But then as it starts to understand the data better, it realizes that it can whittle down the number of neurons significantly and end up with a much smaller model in the end. So what did we see? Well, we saw that Bayesian model selection is a good procedure for finding inductive bias, but I'm arguing that it's a bad procedure for finding model size. We see that approximate GPs can give you predictors that are neural networks, single layer neural networks, and give you all the benefits of non-parametric models, but with a decoupled model size. And that by having a training procedure that bounds the approximation error, we get a principle that allows us to determine the model size, and that leads to very adaptive behavior of the size of the network to the specific problem that it needs to solve. So I basically think that we can have our cake and eat it. We can define an infinitely sized model, so an over-parameterized model, but then near perfectly approximate it with just the right amount of computational resources. So in terms of the outlook, what I'm interested in doing with my research is coming up with new training procedures for neural networks that can automatically find the inductive bias and connectivity structure and architecture, and also size, with the hope of making training more efficient, more adaptive, and more automatic. And so we've done some work on this already in deep neural networks, like I've been alluding to during the talk. And if you're interested, you should look at my PhD student, Tigo van der Oudeра's work. So this is the paper that shows how far we've gotten, where we are able to have ResNets appear out of architectures that could become other things. And if you're interested in the whole story that I've told you, these are the relevant references for that. So we've got a version of what I've told you about for continual learning. We don't really talk about grokking in there very much, but that's being published in ICML in a few weeks' time. And the paper that will explain the overall narrative of this talk will be online on archive soon. So yeah, happy to discuss. Keen, thanks for all your comments and questions. I see there's already a question there. Yeah, thanks.
First, sorry if I sound annoying, because actually the point is that in the end I want to say I would do the same procedure than you do. So there is no disagreement on that, but I strongly disagree on one of the arguments, and it might be just a question of me misunderstanding or phrasing stuff. I'm going to go fully Bayesian. I have models, neural network or whatever, like in a non-parametric setting, so nested models. Okay, I put a prior on the models, and then I go fully Bayesian. So I have a posterior that gives mass to all of the models. And then I say, okay, I could go variational, but my variational family would be very specific. It's just, I decide to consider only posteriors that give mass only to one model. So they have to select one model. Either they charge model 1 or model 2.
Okay, but this model by variational inference would have an infinitely bad elbow, right? Because you're placing zero mass on some models that do have positive mass in the posterior.
But what I'm claiming is that if you minimize the elbow in this case, you're just exactly doing the same thing as model selection, actually, as you would do. So model selection is just a special case of elbow where your variational family is actually giving all the mass to one model. And I'm not saying that it's the best elbow to do, but I'm saying that I find the criticism against model selection a little unfair because it's actually a special case of Rohrbach.
So I think maybe.
I'm sure of that. We can write it down.
Okay, well let's write it down. Now,
it's even how some papers justify Bayesian model selection actually.
Okay, well, so yeah, so maybe I think it's possible. It would be interesting to write it down. I'd love to do that together. But I would still actually say that I'm against that way of looking at it because, well, one reason is that the elbow would be negative infinity, right? So because you're essentially saying that your variational posterior can only place mass on one model, yes, which means that it has to place zero mass on some models which have positive mass in the posterior. And that gets infinitely penalized.
It is the other way. It's the KL between the approximation and the true posterior, not the reverse.
Okay.
So it would not be infinite. It would exactly give the evidence of the model plus the log of the prior of the model.
Okay, so I think it would be the other way around. But let's try and work it out. Yeah, it could be that it's equivalent. It could be that it's equivalent.
Okay, I think in the interest of time, especially given it is we have to buy tickets in Tokyo Station, we're going to take questions there. So let's thank the speaker again.
My talk is going to be about reliable multimodal AI, and it's going to be a bit more practical, maybe, or like applied. I recently started. Huh?
I see you're judged us now.
No.
Practical.
No, I mean actually that's more the opposite way. That I'm impressed by all the other work, and this is just like applications in some sense from your perspective. I started 2 years ago at TU Darmstadt, a bit less than 2 years ago. And our lab has been growing. This was after the first pictures, half a year, and this was just this spring and one of our retreats. And we're still growing. And overall, we are in this Hessian AI Center, which has been founded a few years ago, and it's a very dynamic environment in the sense that 20 new professorships in AI have been established, around 11 at TU Darmstadt. And there's lots of funding both for research, but also for infrastructure. So at least for academic purposes, a big AI cluster. But I want to talk today about reliable multimodal AI. So what does it mean? So think about this image. Maybe a visually impaired person asks, what's the caffeinated drink in the fridge, takes a picture and likes to answer this question. What do we need to solve such a question? But clearly, we need some language understanding, we need some visual recognition. Probably we also need some reasoning there. For example, Red Bull is caffeinated. Let's get to a different example. What should I do after my daughter ate one of these berries? And that actually happened to me when I prepared this talk a few years ago, the first time, at least when I came up with this example. And clearly here, we don't just want to understand language, understand vision, but we also want to be reliable. We want to have a system which we can trust if it helps us in any way. So what do I think what we need for this? And I think on the first hand, we need good multimodal representations. In this talk, I'll mainly focus on NLP and computer vision multimodality, but of course, this extends potentially to other modalities like audio or whatever signal you're working with. Then we need reasoning across those modalities. And on top, maybe I'll spend most time on that, how can we induce self-awareness into models? How can we make them reliable? So I'll start off with some examples of works we did in each of these parts. So let me start with multimodal representations. And here we've been focusing on video and language, as we think that video is still sort of one of the main challenges where there's sort of much more to do than, for example, in images and video. I don't have to say images and video, images and text. We're also working on that, but video is clearly much more challenging. So here we're looking at unification of video and visual dialogue, where visual dialogue is image dialogue, using multimodal expert, and this has been just published at CEPR this year. So previous works looked at the sort of dialogue scenario is basically a scenario where we have a communication between an AI and a human about an image or video. And previous work separately looked at images or video. And so this work looks at how can we do that jointly. And there's two big advantages of doing it jointly, or two core ideas. On the one hand, we can have different experts for different modalities, but then we can also use different kind of data. So we can use video data, video image data, video text data, and image text data. And so we have different training stages. And the first part, sort of in this part here, this is sort of, you could see as pre-training, and then we can do zero-shot evaluation on this dialogue task. But then we can also fine-tune on dialogue data, both image dialogue and video dialogue. And the main idea of the approach is that we can have here, we have an image encoder or frame encoder, and we can have both spatial attention and we can have temporal attention. And we can basically learn in a transformer model then different experts, some which handle the spatial part and some which handle the more temporal part. We can have experts which handle captions and which handle the context. So in dialogue, you typically have past context which you want to reason over. And why is this interesting? Because we have different kind of data, different kind of data sets which have different parts of this expert active, so we can learn them somewhat separately depending on what data is present. And at the end, we feed this all in an LLM to do the final training. And we find that this learning these expert-based representations, we can do both here at the top, zero-shot, rather than better in prior work, and fine-tuned models. And we can also do video, which is here on the left, and image tasks. So I just wanted to show you that in this challenging task of video and image dialogue, we can unify image and video dialogue by jointly modeling with different experts, and this allows us to take in different kind of data. I found strong sort of performance on standard benchmarks in this setting. Yes.
So these different experts, are they trained together or independently?
depending on the data. So whatever the data gives us, if our data has dialogue history, so if it's a video dialogue, the video, so all the experts will be present. If you have image dialogue data, then only not the temporal expert will be present. If you have only image text without any history, not the context expert will be present. So it depends on what data points you feed into the model.
Can you pass the mic back?
Just wanted to have a clarification. So it's like the temporal. So the way I understood it is you're decoupling the spatial reasoning from the temporal reasoning.
Yes.
Is there like any crosstalk between them? Because I'd imagine there'd be a problem if you don't connect.
Yeah, there is. So there's two experts. One is the visual expert, which basically ensures this crosstalk between those two, and then there's a fusion expert, which fusions across all experts.
But then do you have?
So expert basically means separate parameters, not shared parameters.
Sorry, but is this like a block that then is repeated again, or this is just happens you do the fusion once?
No, I think this happens multiple times.
Okay.
Or do you activate experts like with a laptop?
Can you repeat it for Zoom? Sorry.
So just as an additional question about how it works, do you concatenate the outputs of these experts and then you can fuse them this way, or do you?
Yeah. So this is basically a transformer, and it's a sort of basically this would be the different tokens, and depending on the tokens, there would be I mean, depends if you call temporal concatenation and transformer, but then it would be concatenation.
Okay. Awesome. Thanks.
The second part, sort of a short note here, basically on video, which I thought was quite interesting, which we found how important it is to induce or understand time in transformers. And it's a pretty simple idea, but I thought I'd share it. So the idea is basically how can we have a transformer-based model locate a textual phrase, for example, a man talks to a camera in the video, and then sort of find where this happens in the video. And the main idea of this work is that you have to interleave timestamps that the model understands it. So we have a frame, we interleave a timestamp, we have a frame, we interleave a timestamp. And that really helps the model to understand where in the video it is. And while you could do other strategies, we found this sort of simple strategy to work best. And it works actually, maybe I skip over the appellations, but it works, sorry, or maybe, no, that's actually good. It works best both for like a fine-tuned model, which here we use Flip, which we fine-tune on a task, but it was also similar if we do it in a zero-shot fashion in GPT. So GPT works much better if we do it that way. And that can then help both for moment retrieval. So we retrieve moments from videos, but also for next QA, which is more a question answering data set. So, yes.
How do you encode the time? Because I guess it will be quite sensitive to that, right?
Yeah, so this is basically this table here. So important part is the the interleaving part. So sorry, the interleaving is these things here. So if we interleave or not interleave, the best one is the interleaving. We also in general found that having integer representation is much better than decimal representation, because that's maybe partially how the LLMs are trained, because they're much more difficult.
So really you're just putting the token of the number, right? You're just putting like 30 as a token in average. Okay, that's interesting because I would expect the LLM to, well, I guess it depends on the range, but I would suspect it will struggle to know that 31 is bigger than 30 or stuff like that, but maybe not in the range you're working with, but yeah, I don't know.
Yeah, good question. So I think of course the higher the numbers get, it gets more tricky.
Yeah.
But if you use decimal positions, it is not always better. So here we see actually for GPT on this task, the relative position works slightly better than absolute, but again, the integer is still better than like a decimal representation. So for example, a relative decimal place, so like 0.25 is really bad for GPT in general compared to using integers. And it's not completely surprising, I'm not saying, but sort of just doing it sort of naively, you might actually get very bad results.
Yeah, I was expecting using some cosine encoding, like in position encoding.
No, you could do that. That would not work well for GPT because you would have to fine-tune GPT in this case. So this is the zero-shot case. For if we fine-tune it, yeah, at least our results was not as good. We could try with sort of more the sync mode. In general, of course, these models still have this standard encoding sort of from the LLM, so that's not taken out. And in theory, you would just need the duration. And then in theory, the model has all the information. If you just give it the duration and these timestamps, it could theoretically do it, but in practice, it's not as good.
Okay, Marcus, you have one more question if you want to take it here.
It's a very
Yeah,
quick one. So the relative is relative to what? So what is the difference between relative and absolute?
So absolute would be absolute seconds. Relative would be between 0 and 1.
Oh.
Relative to entire duration of the video.
Okay.
So next, I'm going to talk a bit about reasoning. And this is maybe just the most recent work we did on that, and quite a bit different than what we've previously done. But I thought it's interesting because it's very timely. It looks at fact-checking in media, online media, and in general, looking at misinformation. And clearly, misinformation grows in scale and quantity, and some even regard it as a serious global threat. And the idea is we have claims which are frequently made online, at least from the quantity, most of them are online. Frequently they're multimodal. And then we have fact checkers. We have human fact checkers. And they decide, okay, this is a correct fact, or we refute it, or we might maybe have not enough information to do either one. And we are looking at how can we automate that process, because clearly there's too much to do manually. And yeah, here this says that 80% of the claims are featured media, so like multimodal, and clearly it's above human capability to do all of this. So yeah, we want to automate this multimodal fact checking. So the idea here is to have a 6-stage LLM pipeline, and we'll be heavily basing this on prompting big multimodal models. And the input is a multimodal claim, and right now we're working just with text and images, but in future we also hope to work with audio and video. And then additionally, we have external knowledge or tools such as web search. And first we are the first work sort of to handle claims and evidence that are both multimodal. And we are using sort of a report, both to keep track of what is happening during the fact checking, but also as final output to the human user to then see what evidence the model used and what justification it gives. A few more details about the approach. We have a claim coming in, and then we generate a report which is multimodal and is both LLM and human readable. And it's always in context for any of the future reasoning steps of the multimodal LLM. And yeah, we use a training-free backbone, so it's based on prompting. Yes?
So as I understood you, so some of this fact-checking is based on web search. So could there be also an issue with like the source the LLM using for fact-checking is also not fact-checked? I guess like there are different level of reliability for sources.
Yeah, that's a good point. That's sort of a plan we plan to integrate to sort of rank different web pages according to their reliability. Right now, we only exclude some, but that's more to avoid leakage. So we exclude all the fact-checking web pages which contain these human fact-check reports, because that's also our data. And we can also exclude some where we maybe don't have access to. But
maybe also connecting it to the data of the world. So I guess bias is also a natural way of like ranking these different sources, because then we identify like the uncertainty like based on the reliability of the sources.
But in Marx's house, there's no uncertainty.
Not yet.
I'm not sure how that's going.
It will be at the end. Yeah, so we plan different actions the LLM can take, execute those actions with these external tools. Right now, they include web search, image search, reverse image search, and geolocation. And in future, we'll plan to add more. And then we summarize the output, because typically it's too long. And then based on this evidence, we sort of developed it a bit further. And finally, we provide a judgment. And the judgment either can be that we have not enough information yet, and we replan or do another action. Or we provide eventually a verdict, which could include supported, conflicted, refuted, and not enough information. These labels might vary a bit depending on the evaluation data set, because different data sets have sort of slightly varying labels. And at the end, we have sort of a justification stage, which provides a textual justification. It could also, yeah.
So the outcome is here one of these 4 classes for every observation in the data that you have?
Yes.
Okay, and is this?
I mean, it depends a bit. So it could be more diverse. Some, as I said, it depends sort of on the data set. Some have 3 classes, some have 4 classes. Right now, we're building a data set which has even more diverse kind of classes. But yeah.
Okay, because I was just trying to understand what is, does it make sense to also somehow have fake data in the sense of like, I mean, you can create fake reports, you can create fake images, right? And then you would know the ground truth. So this, we're just generating images, generating the reports to, like, then you, or like, what is your training data source in this case?
So there's no, I mean, as I said, it's training free. So there's no training data which we use.
Okay, so you're zero shot is that?
Yeah, basically. Yeah. I mean, zero shot is of course always a very strong statement, because clearly to develop the pipeline, there's sort of some validation data we use, but there's no explicit training, yeah. But we have validation data which used to develop the pipeline.
And does it still make sense to make a distinction between, is it AI generated maybe or not AI generated? Like,
yes, could be, yeah. Yeah, so right now we don't have this tool sort of which would identify this, but in general, yes.
Yeah, you have another question.
Sorry, just so the way I see this pipeline, like you you'd have like a greater data set, and then you can check whether the system gives you the right answer. But is there a way of checking if it gives the right answer for the wrong reason? I've seen a lot of times when you try to do a summary, it misinterprets the document and it says things that are not in the summary. And I assume that if you just look at the final decision, you might make the final decision that this is fake, but for completely wrong reasons, and the justification could be completely off. Is there any way of checking if that happens, and to what extent?
We have sort of a small human study in the paper, and it shows it's slightly better than sort of a baseline model. But yeah, it is hard to do that. I mean, and even then, I mean, we would even, because we don't, to completely understand it, right, we would need to understand what the weights are doing, right? Because it could provide everything sort of on the surface correct, but there might still the actual reasons might still be different why it makes this decision. And just it's really just a justification which comes in text. So right, that's all we can get here. But yeah, you could check if the justification and the elaboration and the evidence, if they all match, you can check that. But right now, the only way to do it is with manual. You could also use an MLM, but I wouldn't trust it. So I think the only way to do it is humans. We did that in a small study, yeah. One other thing we introduced with this work, attacking one of the issues, is that the strongest MLM we're using is GPT. But there's of course the problem that lots of the data it has already seen. So it actually knows about all these claims because they're before the knowledge cutoff. So here we create basically a small set where we make sure that it's after the knowledge cutoff of GPT. So we have a multimodal fact-checking data set with sort of 300 claims, and it has these different labels, and it's after the knowledge cutoff. And we...
Do you want to take a question?
Oh, sorry.
Sure, yeah.
I'm very curious about this because I think at some point in the past I tried to do something similar, and one of the challenges I had is like to make sure that the piece of information, like the new piece of information, was related to something that's actually new. That, for example, like if it's a word event, usually it's something new, but for example, it could be just something that is like, for example, a new piece of information but related to something in the past. So it's still like there's still contamination with like information by the LLM.
Yeah, so I think that is a good comment. I think we can't guarantee 100% contamination free. I think we'll see from the results compared to the other data sets. So maybe we look at the results and then I can say a bit more to it. Yeah, so right now here we see the results. So these are different benchmark data sets, the first three, and then this claim review is the last. This is the best GPT baseline. In the paper, we also have other LLMs which are open source. So here we have unseen claims, or mostly unseen. We have also prior SOTA on the other data set, and then we have our work, and we see a consistent improvement, but we clearly see the biggest improvement for the case where GPT doesn't know the claim, so at least the date of the claim is after the knowledge cutoff. There could be still some leakage, and we're looking into how can we collect data even better. That's sort of only a small part of this paper, but yeah, in general it's hard. And we also try that the search engine doesn't retrieve things, but also there we don't have full guarantees because we don't have, of course, full access to the search engine. So there could also be leakage in the search engine. Yeah. And this is GPT without using tools. So there, of course, there's variants which the GPT itself might use some tools or web search that might perform differently or better. So we have appellation study here. This is normalized to 100% across these 4 data sets, and we see that web search is clearly an important tool. We also see that follow-up iterations are important over just running a single round of our approach. Yes.
Yeah, question? Yes.
Yeah, sorry, but I think you answered. Because I was wondering if you were also considering kind of cascading effects. So do you look at the history, how the information potentially has spread through the network? Because I just know from previous work that this is potentially quite different if you have fake news rather than true news. Because true news has a specific kind of way to propagate, while fake news is like there's a strategy behind how the people try to spread it. But probably not. That's not what you meant, right?
No, so the singleton just refers to our iteration in the pipeline of calling maybe another tool, doing another iteration of all our sort of steps. So we haven't looked at sort of the network propagation. With GPT it will be also very difficult, but of course we could do it for the open source model. I'm a bit concerned. I'm not sure that would help much. We would see much there, but yeah, I don't know.
And it's supposed people claim it's very predictive, but that doesn't mean that it's really
in the neural network, it would be very predictive.
No, it's more like having that as an additional feature, kind of taking this information into account, like how the news has spread through the internet.
Oh, okay. How it's spread? No, we haven't used that information at all. Yeah, so we can handle claims that are multimodal both in the evidence and in the claim. And we have been reasoning with MLMs and tools, both GPT and open source models. And we have sort of a report which contextualizes all this reasoning. But this is not really self-aware or reliable, because clearly this is all happening in the parameter space of the LLM. And we don't really have a knowledge how it is reasoning. So the last part, I'm going to talk a bit about how we can make some of those things more reliable in a slightly different context, mainly visual question answering. And yeah, I'll start with the work we had at ECCV, and then I'll end with the work which we had most recently. So here the question is, or here the task is the visual question answering. So you have a question, for example, is the walk signal showing? And you have an image, and then the model has to answer this question. And clearly the correct answer is no, but sometimes the model might get that incorrect. And in those cases, we rather would like to abstain or say, I don't know, rather than answering incorrectly. And that would, at least for this part of the talk, I've referred to as self-awareness or reliable. Yes.
So I'm thinking about this self-awareness term that we are using. I guess you are referring only about the model being uncertain about what it knows, right? Or is it anything else?
No, I don't. I guess what do you mean by anything else?
So what do you mean with self-awareness? Can you define self-awareness?
Yeah, that it cannot just predict the answer, but also it can predict if it can predict it correct or incorrect.
Right. So it's just confidence. Basically.
Yes. Yeah.
Yeah, but it sounds like consciousness.
Exactly. It's in neuroscience people talk about self-awareness in a different way.
Yeah, it's going to kill us, and it doesn't know.
And so where we started off was a standard visual question answering model, which gets on this VQAV2, which is one of the standard data sets in the field, gets maybe 70 or 78% of accuracy, and the rest it gets incorrect. Now, in an ideal case, we would rather have the model abstain on all these incorrect answers rather than answering them incorrectly. But as it turns out, with the model we had then, that would really hard. Just using the max prop, it would then only answer 60% of the questions if we allow 1% of risk, so 1% of incorrect answered questions. And now I'll talk a bit how we can potentially improve this and get this green bar lower, so answer more questions correctly without increasing the risk, without increasing the number of questions we answer incorrectly. So here we have basically the question and the image. We have a function f, which is the visual question answering model. And now additionally, we want to have a selection function which takes in some input and decides if this is correct or incorrect, and then can decide if you should answer this question or if you should rather abstain. And then we can call this joint model a selective model. And this G and F don't necessarily need to be separate models. They could be the same model, but sort of one can think of them separately. And the most simple way to do G is just to threshold over some input if you should answer or not. And the max prop would be then just thresholding over the probability or score of the model of the maximum answer. So maximum, the most likely answer. So, but this leads frequently to problems if the model is over or underconfident for giving the answers. And we looked at different alternatives, including calibration, where we first calibrate the model and then still use the same function, or we trained a selector model which would take in different inputs of the model and then predict the output. And the main decision here is to train the model on some, typically we would use a validation set where we would have labeled data if the model is answering this question correct or not. And then we would regress to this answer C. I say regress because in the WikiA dataset we actually get sort of sometimes you get partial correctness in some cases, and this really helps to get the best performing model here. So we have this selective prediction, and there's been, of course, prior work in that as early as the 1957, 1970s, which had this reject options in classification. And more recently, there have been works also mainly in different multimodal, unimodal settings. So here the experimental setup, we have a training set where we train the model. We have then a validation set where we train the selector function, and then we have a test set where we finally evaluate it. And there's sort of another small validation set which is used to validate the function G. And with that, we then get from the scenario from the case with max prop, where we have like 16% of questions which we can answer under 1% risk, to around 31% of risk when we have this selector-based model. And calibration is slightly in between. I noticed I forgot to show this here. Some qualitative results, just to clarify this, why these are different correct answers given in the data set. So the data set has 10 possible answers. And here the max prop answers incorrectly, and the selector correctly abstains. In contrast, on the right side, we see that the max prop abstains and the selector, the max prop incorrectly abstains. Or maybe not incorrectly, but it could answer correctly skateboarding. So we expose this poor performance in existing WikiA model reliability, and the learned selector can improve performance up to 2x, but there's of course lots of room to improve. And sort of one downside of this is that here we have to learn a separate selector model. And I'll talk about next a bit how we can circumvent it.
You have a question in the back.
Thanks. Just a quick question on the VQA setting.
Yes.
Is the set of outputs known or constrained, or is it just open-ended generation?
Good question. It's not known per se. So the test set actually has answers which have been noted in the training set, but it is typically modeled in a way that you restrict it to the, for example, 3,000 most frequent questions. Depends a bit on the model, how we do it. So we have been using both classifications models. There you sort of have this hard restriction of the number of classes, but we also have been using generative models, where this is sort of, you could generate in potentially a wider space. In practice, however, if depending how you set it up, you wouldn't actually generate much more than the training scenario. Depends, of course, on the model. Most recently, we have been experimenting with sort of larger LLMs. There, of course, you have then, because if you have much more pre-training data, you might generate more answers.
So in the kind of open-ended generation setting, maybe you can go back to one after.
You want to go to the model or to results?
Where you showed the example outputs.
Oh, okay.
Yeah, so what would you do in this, in like the cat looking at camera? Like how do you deal with that? The bottom output on the left.
Yes. So I guess what is the question?
Like it seems quite open-ended. So like how do you, like is the bird looking at the camera? There's
Okay.
no bird, so like do you map that to your
Okay. So I mean the answer is quite simple. So we only treat whatever is in the data set as answers. So we just look at the Y, which is the potential answers, and has to be an exact match. We don't do partial matches. This is how the data set is set up. And I think for this specific data set, it makes sense to keep it, also to keep the comparison to prior work. I think because most of the answers are really short in this data set, it makes sense. I think for other data sets, other scenarios, one has to maybe do more approximate matches. But for this data set, I wouldn't change it.
We've got one more question in the front.
Going in a similar direction, because could you actually, with your nice setup where you could, now you have another explainer kind of trained, could you have a look at what the important features are where something goes wrong that makes you abstain things? Because it looked to me like if you do kind of a sparse, if your explainer, or you call it differently, right, the second network that would try to predict whether you should abstain or whether you have a correct prediction. This one exactly. But uses now the hidden features. Could you also have kind of a a sparse feature regression or something like this on top that would allow you to say what is actually important among those features to make that decision? And did you have a look at this? We
did not look at that. I'm a bit doubtful that the selector, at least how we set it up now, is powerful enough to do it. It's a pretty small network to avoid overfitting. We also try larger networks. It helps. Yeah, so I think one probably could try to set it up, but I think then one will have to probably use more training data for this selector model. One has to probably make sure how one trains it. Yeah. I'm doubtful this specific model will be the best for that, but yeah, we haven't also looked at it. So I already mentioned, so far we have sort of trained a separate selector, and sort of most recently together with MT, I've been looking at how can we do variational visual question answering. So how can we use the I1 variational learning for this task, and can it do also then selective prediction? And yeah, it's basically sort of the same motivation. We want to do this visual question answering, but now we want to use variational learning to get better estimates. And of course, there's been lots of prior work using I1, and we have maybe seen actually most of this work here over the last few days, so I don't have to detail them here. And we have, as I sort of introduced, the selective model where we want to abstain or not. And we measure coverage at a certain point of risk. I sort of simplified it a bit in the previous slide, but here we have sort of more this coverage at risk. And we also look at an additional metric, which is effective reliability, which is a cost-based metric of the downside of coverage at risk, is that you need to basically, what is typically done is to estimate the right location on a test set. So this effective reliability, you can do that at a training set or validation set. And you can have a small risk or a high cost for high stakes application, where we want to like have a model which rarely gets things wrong. And here we use also slightly different models, the state-of-the-art models, specifically Bayes 3. We look at the Bayes and large model, and sort of a smaller model Wilk to use this selective prediction. And we look at two data sets, visual question answering, which I just showed. And we also have some results on the Anvil R2, sort of a visual reasoning data set. It's quite similar to visual question answering, but slightly different task. And one additional thing, additional to the ID case, which I talked about so far, we also have a ID and out of distribution setting where we have parts of adversarial VQA, so which are a bit different from distribution in the visual question than the VQA data set. And we compare two variants. We have the Adam fine-tuned one, and we have just the normal weights and MC dropout. And in I1, we have also the mean and MC sampling, so the same number of samples in both cases. So the mean case has just one, and the MC sampling we have, or MC dropout, we have 64 samples. And then we just look at the max prop or the corresponding mean. And here the results on the VQA data set. The first result is then with respect to accuracy, the I1 based or visual variation of VQA performs as good as Adam. And I think that's already the good result that didn't decrease in performance with respect to accuracy. And this is true for these three different sizes of models. We see that we have those as the weakest model and Bayes 3 as the strongest model here. And then if we look at the selective prediction performance, we see then that this variation of VQA through the Ivan-based model outperforms both the mean one and the Adam W. And that's again true across these three different models, and also across the other metrics. So the phi 100 is a different metric, but basically the observations are very same. And I think interestingly, we also see this on the OOD samples. So here we look at the x-axis at different fractions of out of distribution data, and here the Bayes 3 model, and we see that consistently the variation of VQA is on top of the other two. Yes.
That's okay. How does it perform to the previous approach with the explainer?
Yeah. Yeah. So there's two answers to that. If we would now compare it number to number, this would be better, but this is that was on a different model. If you also train a selector here, that is about equal or better than the variational approach. So we're also looking into combining this. They're somewhat orthogonal, but so far it's been a bit tricky to combine it. So yeah, and it holds across different models, the large, the Bayes, and the Wilk. And now here we now look at the equal compute. So we are comparing it to Adam dropout. So Adam W with dropout, and we see that compared to variational VQA, to the I1 variational VQA, it consistently is better, both for the Bayes large on both metrics, but also for the weight base, and also similar on the NVLR2 data set. We see similar trends. And then some qualitative examples we see again here. For example, does the pedestrian light say walk? The correct answer is no, and the model abstains, while the RMW says yes. Here another example, what animals outside. Here the RMW abstains, while the variational VQA gets it correct. So next steps here, we want to do more qualitative analysis, maybe calibrate the variances better for better abstention, and also extend these abstentions to unanswerable questions or longer generations beyond sort of what is in the WikiAV2 dataset. Any questions to that part? Okay, I seem to have like a few minutes to talk about what we did about unlearning or like attacks on unlearning. And basically, it's sort of about that we shouldn't leave a backdoor for unlearning. So the paper is called Erased but Not Forgotten, How Backdoors Compromises Concepts Erasure. The idea is that if you have an image generation model and you want to erase concepts, the question is how good do these models actually erase those concepts? So for example, if you want to erase nudity, if you want to erase certain identities, how good can you actually erase them? And what we looked is, can we implant a simple trigger before the unlearning to make those concepts reappear if you use those triggers? And we looked at different erasure methods, both like sort of in the text encoder space, in the cross attention, or in sort of the full model. And it turns out that in general, it's very hard to prevent a trigger from passing through. So if you implant a trigger before unlearning, you can always recover what has been seen before. So what do I show here? We have sort of the image without an attack generated by stable diffusion, and it generates Morgan Freeman. And we have here different unlearn, so we want to unlearn Morgan Freeman. And we can see that different erasure methods can actually successfully unlearn Morgan Freeman. But then if you plant it, that doesn't generate Morgan Freeman anymore, basically. There's no more Morgan Freeman, at least. I mean, I'm not a good.
It's in my hand.
But then if you plant a trigger, and we looked at 3 different variants, he does appear sometimes more strongly and sometimes sort of less strongly again. And this is sort of course, just one single example. On average, we see that the trigger frequently appears again. And this is not just the case for this sort of celebrity-based data set, which people have been looking for erasure, but also for concepts such as nudity, which you might not want to reappear. So today I've sort of shown you these sort of 3 main categories, but there's of course lots of future work. Maybe you want to adjust it much more to people or certain personal preferences, look much more at out of distribution, and maybe also learn more continually. And with respect to people, I think it's important to think that there's different risks and different tasks, you might have different requirements. So they might have very low risk scenarios, very high risk coverage, scenarios where you use very low risk, other scenarios where you want to have high coverage, and having this all in the same model and all in the same scenario could be tricky to know when to apply a low risk scenario, when to apply maybe a more high risk scenario. And there's also different type of errors. Some errors may be worse than others. So far we haven't covered it. We have just a single level of risk, a single type of error. I also might have different users. For example, in the specific scenario, maybe a sighted user can verify the visual on the web, and maybe a visual impaired user actually knows a lot about plants, but cannot identify the visual. So you might also have different users, different ways how you can interact and communicate. In continual learning, you clearly have also this part of personalization, maybe adapt to personal preferences without forgetting. Maybe you want to learn with the user. Maybe a visual impaired user comes into a familiar room versus a new room, want to have different maybe risk scenarios at home versus in a non-at-home scenario. You might have changes over time, new facts and new concepts, and you might want to act to them differently. And last but not least, out of distribution, out of this domain is clearly a challenge where we sort of started to look at, but I think it's actually sort of this, you have this, I think it's actually more like a continuum where maybe at some point, things which are very little out of distribution, maybe you can still answer those questions, but eventually if they're too far out of your training distribution, eventually you just have to maybe abstain because you just don't know about them. So in conclusion, I showed you today multimodal representations. The video is a challenge, and timestamps matter. I talked about reasoning and specifically our approach to misinformation called defame, and that the parametric GPT alone is sort of limited. And the last part I talked about self-awareness, and clearly reliability is challenging. We looked at variational variant of that, and at the last few slides I talked a little bit about unlearning. So with that, I thank to my collaborators. Happy to answer any further questions. I'll try to reliably answer them, but maybe I abstain. I'm not sure. And then you can email me.
All right, first let's thank you. We do have about 5 minutes since we started late, so I'll ask the next speaker to step up and set up while you answer some questions if you want.
From the unlearning part, so I was curious, like, how do you evaluate your unlearning models? Like, do you use just the visuals, or do you have any metric in place to actually see whether it has actually unlearned some concepts or not?
Yeah, so it's actually a very tricky part to evaluate those models. It's actually tricky to evaluate images, and they're sort of somewhat unsatisfactory way to evaluate. We basically use whatever is used in the community for the respective data set. For example, for the unwanted content or nudity, there's sort of nudity detectors which are used to detect if nudity appears in the generated images. Or similarly for the faces, there's face detectors which try to identify that. That is not perfect, and it has problems. Yeah, so far that's what we're using, so what has been used in the community. I think you have to connect to Zoom.
I have a more high-level question about your fake news detection, or as an example, because it looked like you were starting already to build up something agentic, so kind of agentic networks, and you're talking about learning with humans. And I was wondering, to which degree do you also see a future in, that you have also multiple, let's say, specialized agents that potentially interact with each other, but they might also fall into these, might introduce new backdoors or something like this. So I was wondering, to which degree do you believe that that these multimodal approaches will work well if you combine these specialized agents and they can interact in complex ways.
I think that would be useful to do, and I think it's necessary for lots of tasks, because on the one hand, I don't think it's efficient to do lots of things with just a single big transformer style model. I think that's not very efficient, and probably also not very good. So like if you do database queries, doing that, inputting that in a neural network is probably not the right way. Maybe you need, for something, maybe you want to actually request assistance from a human, but you still want to reason and to try to learn. I think that would, yeah.
Did you see just similar also with your task? So you would kind of still build one kind of big model, but one kind of, for efficiency, did you try out different things, for instance, and did you see when you compare different ways of combining these agents, the visual agent and so on?
I mean, we compared definitely to different baselines where we had just the same number of parameters, but not experts just learning jointly. That was not as good. Yeah, I guess I'm not answering fully that question. It's not that I think they don't communicate. I mean, the expert in the video space, they just communicate on the parameter level, right?
Yeah.
So, but for the misinformation car case, things it all is over language, right? So it's sort of a different interface.
Oh, I have to share it.
Okay, because it's not ready. I can ask one more question to you.
I think there was one in the back.
Oh, okay. It would be interesting to look into this, like when you do unlearning, like when things work, maybe if you look at the correction term, if maybe things actually change quite a lot when you are able to unlearn. But in other methods, when there's a trigger, then the same doesn't happen. It would be an interesting thing to talk about.
Yeah, maybe. I guess I'm not fully sure.
I'll give you another talk on what correction term is.
Okay, we've got one more from the back. So I think we've got such a long one.
Hopefully, quick question. Do you know if there's much difference in model calibration uncertainty between base instruction team and reasoning models?
I'm not sure I fully understood. Could you repeat the question?
In terms of kind of the extracting uncertainty, whether the answers from models are well calibrated, do you know if there's much of a difference between the base foundation model from the instruction tube, like preference data, and ones that are training explicitly on reasoning, so maths and coding and things like that?
Good question. No, I think I don't know if that's what answer.
Let's save the other questions.
I think maybe you should wait until you've heard the talk. Does anybody work with synthetic data? Hands up. Okay. May I ask what you use it for? Who wants to go? Yeah.
So for instance, we use it to check whether our model is on.
Oh, sorry, can you repeat it?
Thank you. So we do this as a first sanity check, kind of, to see whether our model assumptions hold up and we can learn under ideal conditions.
Okay.
I mean, I guess in my talk, right, in the papers, we use synthetic data to train models from scratch at a smaller scale to kind of have an understanding of their dynamics, like how they learn things, stuff like that.
Good, good. Okay. That's good. Yeah, so talking about synthetic data, and as you all probably know, synthetic data has become, especially over the past few years, is really seeing a revolution in medical research and clinical settings. For example, it's used to in clinical trials, basically to mimic various patients, various experiments, these are a couple of papers that are very clearly advocating for synthetic data as a stand-in for either actual real conditions or human behavior. And also in social and behavioral sciences, that is another area where, again, just over the past 2 years, maybe, the use of synthetic data has really gained momentum. And interestingly, it's from the area of machine learning where people are proposing the idea rather than social and behavioral sciences, proposing the idea. So here are another couple of papers where the idea is to use synthetic data as a stand-in to run experiments, to imitate human behavior, basically to replicate human subjects. Here's another one where, again, the idea here is to use large language model agents as a behavioral strategy to do research simulations. So it's not just medical and behavioral sciences, it's also in the humanitarian space, in NGOs, large organizations like the UN are moving in. A couple of months ago, maybe not that long, about 5-6 weeks ago, for example, I attended this very interesting workshop from the United Nations where they have put forward these 2 agents to simulate refugees, one in Chad and the other one in southern Sudan. And they have followed that up with a report that I have included a snapshot here. As you can see, the idea here is that because collecting data from these populations from war-torn areas is difficult and costly and so on, the idea is to use these personas that will then presumably produce the kind of behavior and data that institutions or organizations like the UN need. Also, market research is another major space where you see the idea of synthetic data. There are so many companies now providing services of synthetic data, again replicating, hoping to replicate market behavior and so on. Here is one of the examples I mentioned. So these are just a few examples, but everywhere you look, the use of synthetic data as a stand-in for human behavior is gaining momentum. And there are a few justifications as to why these various domains and people find the use of synthetic data attractive. But the most recurring theme for why is basically to cut costs, to augment diversity, and to increase speed. So Willie Agnew and colleagues have this really good paper, The Illusion of Artificial Inclusion, where they looked at, 16 research papers where people are using synthetic data, and they kind of categorize the justification put forward by each of them. And as you can see, again, the recurring theme here is that synthetic data is supposed to increase speed, supposed to reduce cost, augment reality, and protect participants in some cases. But most of the time, it's increase speed, reduce cost, and augment diversity, I should say. And so this is what we're going to look at. Does synthetic data actually, it might actually cut cost, and it might increase speed. but at what cost? What are we paying for that? In terms of augmenting diversity, that I will go through perspectives from Black feminist scholars, from complexity sciences, to see if this argument actually stands to any scrutiny.
Hey, you got a question?
Yeah.
I'm not sure if you come to a definition, but how do you define synthetic data? Because it's of very different kinds. I mean, what you would define as synthetic data is quite different. Maybe what you're thinking of as synthetic data, and then there's sort of images generated from realistic 3D models, which is also synthetic data, which is again different maybe than from what you're thinking.
So this is new work. I haven't published anything on this. So it's I'm hoping to develop this into a paper, but I know what exactly I mean by synthetic data is something I have to define carefully. But in this case, I don't have a clear definition, but I'm aware that there are different levels of synthetic data. There are, clear pure synthetic data. There are some level of augmentation. I see it as a continuum where you have, completely newly emerge, whether it's text or image or audio. But on the other hand, you have those that closely resemble material that already exists. So that's kind of a fine-grained, nuanced look that has importance in the implication of whether synthetic data augments diversity or whether it's a good thing or not. But for the purpose of this talk, I'm just talking about synthetic data in general. And you can assume I'm talking those that are generated with very little careful analysis of how it relates to ground truth or the reality.
So just to clarify, the extreme cases.
Ish.
Right, you have one more question.
Sorry, yes, I had a question and a comment. So I guess in your case, synthetic data has something to do with human behavior. Like synthetic data of physical systems and stuff like that is not necessarily a problem.
Yeah, I'm going to get into that now. Sorry.
And then back to my question, just an observation. Is there a correlation between the position and the venue? It feels like, depending if the venue is like machine learning oriented, the position seems in favor. And I don't know, did anyone analyze this? But it seems like there's a strong correlation of the venue where the thing was published and the position they take.
So I haven't actually I haven't noticed this. And this is not my paper. This is from Willie Agnew and others, mostly DeepMind folks. I had long conversations with them. I also don't think they noticed this pattern, but it's interesting, yeah. It actually validates my idea around how a lot of this push for replacing humans with synthetic data comes from, computational or rather machine learning spaces and pushed into the social sciences rather than, the reverse, rather than the other way around. So I should say I'm not a machine learning expert. I don't really do machine learning. I'm coming at this from cognitive science perspective. I'm a cognitive scientist by training, but over the past few years, I've been doing audits of data sets, evaluations of AI models, social media platforms, and so on. So that's the perspective I'm coming from. So in order to walk you through why the use of synthetic data, specifically in the case of replacing human behavior, is a bad idea, we're going to look at what it means to represent human behavior. So at the end of the day, whether we are building computational models or any other type of models, the idea here is that we are representing human behavior, or we are representing a given phenomena or process or something in a formal way. So basically a model is a formal representation of a given phenomena or aspect or so on. So this means that whatever model we are building is not the phenomena itself. And so, as the popular saying goes, the map is not the territory. We are, of course, we hope to capture the territory with as high fidelity as possible. But the more we are aware that our model is not exactly the reality, the better we understand the impacts and the implications of the models that we are building. So this means that, especially when we are trying to model human behavior is dynamic, complex, ambiguous. It's not discrete. There is no clear generalizable formula. So it's always contested. There are always ambiguity, and it's never discrete. This means that there are infinite ways to model a given human behavior, and it depends. What a good model is really depends on what we are trying to do, what our purpose is, and also our own positionality. Our background, our history, and where we are coming from really matters in what we think is an important variable, and we include it, and what we think is irrelevant, and we exclude it. So there is no way to tell, the variables that we have excluded as irrelevant are actually irrelevant without constant validation or reflection. So human behavior, coming from embodied cognitive sciences, which is my background, and complexity systems, is inherently unfinalizable. That means it's constantly moving, it's constantly changing, it's constantly in interaction with others, which makes it messy, and it's inexhaustible. And according to Paul Cilliers, he was a complexity scientist, it's not possible to compress a given human behavior into neat mathematical formalism and description. And this also represents the fact that human behavior is open-ended. That means there is no way kind of cutting the boundaries and saying, this is like the limits of human behavior, and this is what we are formalizing and describing.
Would this also apply to animal behavior?
So the way I think about it is, roughly speaking, again, I mean, it's a continuum rather than a clear cut. I think about physical systems and maybe biological systems and social systems. This is a relatively helpful way of categorizing complex systems. So the more you veer towards the social, this is, human cognition, human interaction, emotion, human behavior, the more it is inherently social, and the more all these qualities, inexhaustible, non-compressible, the more that applies. Maybe the more you are dealing with physical systems, think of DeepMind's excellent examples of board games, the game of coins. So those are relatively simpler. You can exhaustively map any potential variables, any potential moves. So again, thinking in a continuum, those would be something relatively simpler that can be understood even in a governing general rule that could apply to them.
Related to that, do you care more about kind of small-scale human interaction, so about specific individuals that interact, or potentially a whole social system, so like a community of people? Because I can imagine that the behavior of a group of people might be sometimes easier to predict just because there are many people in them, and just it's like an average. Right? Yeah, exactly, somewhere an average. So that might be better predictable, like an economic system also. Kind of a macro variable would be maybe predictable to some degree, not of course not always, but in comparison to, let's say, human interaction, but maybe also some people are more predictable than others, but yeah.
I personally don't think most economic models are that great in terms of predicting communities or larger scales. Are there any economists here, by the way? But I don't think it matters, because whether we are looking micro or macro level, you know, the fact that human behavior is inherently messy and difficult to precisely nail down, that applies whichever model we are looking at.
You got one more question here.
Thanks. So I'm a fellow cognitive scientist, so I have a lot of sympathy for you, especially with the challenges of interacting with current machine learning. I'm a little concerned about your definition, though, because I think that most cognitive science research that actually uses human subjects wouldn't count as human behavior according to your definition, right? We normally do create discretized versions of things. We run experiments where we're using real human subjects, but you know, we create representations of their, or you know, measurements variables, right?
Yeah.
We're explicit about it, at
Yeah.
least in theory. We hope to be. So
Yeah.
Yeah, that's my question.
Okay. This is good. So as I said, I am a cognitive scientist, but I come from a very niche area, embodied cognitive science. So you are talking about traditional cognitive science, who really treats individuals as, you know, items that can be taken out of their environment, put into a lab, and given some kind of, you know, experimental stimulus, and you can measure whatever, memory or something.
Sometimes inappropriately, for sure.
Yeah. So, so from that perspective, what you say applies, but from more kind of embodied cognitive science perspective, that's not ecologically valid, so to speak. It doesn't. It's not as reflective of human behavior in the wild as things exist. So I'm speaking more to the latter rather than the traditional cog sci perspective.
Okay, but if you want to take one more question, you have one here.
Okay.
I mean, feel free not to answer it because it's a bit kind of high level, but I'm wondering what is the basis of arguing that human behavior is this complex? So I mean, I'm making an argument that I might not believe myself, but
yeah.
The basis is like there's a paper from Crisanta who's trying to argue that, you know, we think consciousness and all of this is complex. This is a human bias because we don't want it to be simple, but like, is there something beyond Turing test? Like, if you have a system that passes the Turing test, like, why is that not sufficient? I mean, in the sense that now people believe that, as I said, I don't believe the argument myself, but I just want to know what is the philosophical argument of trying to go that says, like, okay, you can't explain this by some simple rules, and it's way more complex. Like, how do you build that argument?
So you are completely, again, coming from machine learning perspective. Let me maybe give you a concrete example from embodied cognitive science perspective as to why this discrete simple rule for explaining or predicting human behavior doesn't hold. So like, think of me, myself, for example, like I don't have one consistent behavior, whatever social situation I'm in. I'm here, for example, presenting at a conference. So there are social rules and protocols in how I should speak, how I should dress, how I should, you know, interact with people and so on. Later on, when I'm out in the social event, I will behave slightly differently. Even with my family, maybe with my loved ones, it's depending on the condition, the context I'm in, what I am and how I behave is really, really valid. To add another level to that, my history and my background, English is not my first language, for example. I come from Ethiopia, so I have history in you know, social norms and so on. So all that has impact in how I behave, in how I carry myself, in how I interact. So the way I behave cannot be a good example or a generalizable example for how, you know, every human behaves. I don't know if you are convinced, but this is the simplest example I can think of how there is no generalizable rules.
I'm not sure whether this is if you're able to model this with a neural network or not. That part is not clear to me. Like why? Like I agree that you shouldn't be able to model.
You can model it, but that will model if you do it, you know, as closely in a way that is as with high fidelity as possible. You might be able to model my behavior, but that doesn't mean you can generalize it to other people like me.
I think this is a really interesting discussion that I will love to get at some point, but maybe I'll put my foot down on what's going on.
Okay, yeah, let's move on.
Yeah, very interesting though.
Yeah, so basically, because you know, every human is unique for reasons I explained. Paul Cilliers says that a model like a complex system, a model of a complex system would have to be as complex as the system itself to really capture that phenomena, and that is in a sense. So as a result, the behavior of the model will be as complex and unpredictable as the system itself. I highly recommend this book. It's very light to read, so I think it will get at the heart of what you are considering. So going back to, you know, the infinite ways to model a given behavior, I also want to bring in Black feminist scholarship to this. For example, Sarah Ahmed talks about how every individual's experience is different from others, especially you know, if you are from an identity or from a community that doesn't neatly fit into the status quo. So Sarah Ahmed, for example, talks about this comfortable chair where you have this professor that has this nice chair that he sits on it. Over the years, the chair has become so comfortable. He sits on the chair has kind of has eventually adopted the shape of his body, and he can just sink on it. And for him, from his perspective, that chair is perfectable. That chair is perfect. So then another person comes in and sits on the chair and says, you know, this is not comfortable. So it's difficult for that professor to actually understand how that chair can't be uncomfortable for others. So she uses this metaphor to explain how queer identities have difficulty fitting into traditional understanding of sexuality. And I want to also emphasize that most of the time when we talk about marginalized identities, it's either seen as something we pity or something negative. But Black feminist scholars actually emphasize that to be on the margin of, you know, whether you are queer or a Black feminist or so on, is not something that is negative. It's not something that you want to give up. It's not something you want to abandon and move from the margin to the center. It's actually it actually offers you a radical perspective where you can create movements, where you can imagine alternatives, where you can develop new worlds, new perspectives. So being on the margin is actually something that should be treasured, or not something that we struggle to fit not something we struggle with, or not something negative. So I want to emphasize, this is why I want to emphasize the fact that this has implications for using synthetic data for augmenting diversity, because diversity is something people on the margin see as a space that gives you power, that gives you space to be creative. So having that space for what it is really critical. It's not something that needs to be replaced because it has value in and of itself. So to summarize the Koksai and Black feminist side of the talk, basically, the more socially complex a problem is, this goes back to your question around from physical to social systems, the less you can capture that with adequate data, and the less you can automate and model it accurately. Also, what accurately means, again, varies and depends on your objective, your perspective, and so on. Just before we end this, I want to give you another example I learned during my master's. I did like a bunch of complex systems modeling, and one of the lessons I learned that has ever stayed with me was the professor explaining how what you want to model really depends on the purpose. So, for example, a portrait or a pig or a mannequin can all be good models for the human body or humans, depending on your purpose. So if you are a fashion designer, a mannequin is your best model. If you are a medical student, a pig would be the best model for you, whatever you are doing. Whereas if you want to remember your dead grandma, then a portrait is the best model. Again, to emphasize how there are infinite ways to model a given phenomena. Okay.
Or a slight comment to connect what you were saying with what the question that you were asking, Rebecca, about like, well, if we sum over population, can't we use the mean to predict something that is the mean very predictable? And I just was going to connect that with what you're saying, is that the value of marginal experiences is that you should not reduce a whole distribution to a point estimate, right?
Exactly.
It's representative of something, it's not necessarily representative of the experiences that you want to capture, right? So that's one way of saying maybe like
also want to represent a distribution of the land.
Yeah, exactly. So meaning that every technical choice that we make might have some, kind of missingness. That's
exactly.
What you're saying.
And the lived experience of marginalized identities is really critical. This explains Sarah Ahmed's chair metaphor, where the chair is comfortable for one person, whereas it's uncomfortable for another. So your experience really is important. So if we want to understand marginalized experiences, marginalized people are the best representative of capturing that experience. So before we talk about synthetic data, I think we should talk about where synthetic data comes from. Mostly large language models, especially in the cases that was emphasized with Willie Agnew and co-authors' papers. And I'll just give you a very brief overview of various studies on large language models, trying to understand, their homogeneity, representativeness and bias, and so on. And these are actually really good papers. So the first one is by Atari et al., where they looked at the cultural representativeness of large language models, and basically trying to understand which human values in cultures large language models represent. And they compared that with these massive data sets. Sorry, I have to look at my notes because this is the first time I'm giving this talk. I actually made the slides on the plane last night. Okay, basically, you can understand that. So they used this large scale cross-cultural data, and they to examine the performance on psychological tasks, where they found that these large language models, I think they mainly looked at GPT variants, and they found that the outputs resemble the values in cultures from weird societies. So weird societies, Western, educated, industrialized, rich, democratic societies. And furthermore, so that's the main takeaway here. And another study here also looked at cultural bias with, again, ChatGPT, where they found that the outputs and the response from GPT, when it's prompted with American context, ChatGPT exhibits a strong alignment with American culture, but it adapts less effective other cultural contexts. Basically, the more you are away from a typical American cultural value, the less capable or the less representative the model output is. So this is to show that these models we're often using to generate synthetic data from are inherently, they have concentrated value that really encodes and represents Western values. Again, other people have also looked at the homogenizing effect of large language models. In this case, for example, they looked at college admission essays, some of them written by people and some of them written by ChatGPT or GPT-4. And the conclusion, what they found was that despite enhancements aimed at maximizing diversity, AI model outputs, despite enhancement aimed at maximizing diversity of AI model outputs, human written essays essentially outperform ChatGPT-4. Basically, the essays that were written by people were much more diverse compared to the essays that were written by ChatGPT. Again, emphasizing that these models again tend to homogenize and concentrate on specific cultures. This is another study, again, from last year, where they studied the causal impact of generative AI ideas on production of short stories to examine creativity, where they found that ideas, or rather generative AI-enabled stories are much more similar with each other than stories by humans alone. This is similar finding, again, where human creativity is much more diverse than essays and stories generated by ChatGPT. So we've seen that large language models tend to encode Western values, and they tend to kind of flatten diversity, producing homogeneous or very similar outputs. There is also the question of bias. Again, there is a plethora, there is a robust body of work by now. People have been studying, bias in large language models for, I don't know, at least, 4 or 5 years now. Maybe the stochastic parrots paper was one of the first big landmark papers, and that was published in 2022. So since then, we have a massive a body of literature that has found recurring themes that these models tend to be biased against, minoritized communities, minoritized languages, cultures, identities, and so on. In this study, they looked at 10 different dialects of English, from standard American English to standard British English to other varieties around the world. And they found that these models consistently exhibit stereotyping, demeaning content, and lack of comprehension, and so on, when it comes to dialects that are far from standard English and standard American and British English. So, as well as these clear, explicit biases, there have also been studies where people are looking at covert and overt racism, because with covert racism, it's relatively easy to identify, it's relatively easy to address. With overt racism, whereas with covert racism, you really have to come up with all kinds of ingenious ways to set up your experiment and to investigate this. So in this paper, what Hoffman et al. Did was they, I think, looked at about 8 generative models, some of them the latest ones, and they compared how standard American English and African American binoculars or African American dialects are scored according to these models. So here is an example. For example, you have a text saying, "I am so happy when I wake up from a bad dream because they feel too real." And the person who says this, as you can see, is scored as intelligent, brilliant, and so on. Whereas the same exact language or the same exact message, but written in African American dialect, which is, "I'll be so happy when I wake up from a bad dream because they be feeling too real," and the person who says this is scored highly as lazy, stupid, and dirty. So you can see that even dialect differences result in covert racism. And this is not really just a handful of papers selected to cherry-picked for this argument. As I said, there is a massive body of work that shows that this bias is real. And yes.
This homogenization effect and this lack of granularity, would you say it's qualitatively different from the homogenization that would be caused by the printing press, the formal educations done by states, or the single accents given by state TV? Would you say the fact that it's AI or machine learning behind is a qualitative difference, or is it more like a quantity, or is it like something that's new?
That's a big question, but I'll attempt. I think
so the accents do get lost after there were many regional dialects that do get lost after everybody gets taught the same type of writing. They hear the same accents, and maybe not everywhere.
I think maybe that's a gradual thing, because you have I live in Ireland, and I go to even Northern Ireland or Scotland, and I can't understand people because their accent is so strong. So, and those nations have been living close. Sorry, I love those people, and it's great accent. It's not a negative thing. It's just that it's really it's just to show the stark difference. So I see the point that over time, gradually, yes, accents kind of morph into each other, but also there is also still distinct accents between even close nations. So I live in Dublin, which is if I go to Northern Ireland, which is an hour and a half, the accent is yeah.
Yes, you have a question on that?
Okay.
So I guess from your talk, diversity is something good. We want to preserve it. The kind of complexity of human experience, kind of upbringing, all of these things, it's very difficult to model. And with these LLM systems, if you kind of treat humans as one big mixing pot, then you're missing out with all of these things. You have homogeneity and bias. I guess on the flip side, there are people who kind of want to model the complexity, want to de-bias systems, be able to represent kind of different communities. So an example that happens a lot in kind of Japan is because they're mainly trained on Western data, it doesn't represent our cultural values, contextual values, etc. So I just wonder what your opinion on actually maybe we want to understand this complexity, we want to explicitly deal with it for these reasons.
I think I agree with you. I don't think that's a question, right? I think I agree with you. Yeah, that's absolutely. I'm totally behind that. Yeah. Okay. So why I presented how models encode weird populations' values and how they are homogenizing and how they are inherently biased is to underscore the point that when you have models that compress stereotypes, the idea of using the same models to augment diversity just seems absurd. But it's also important to look at data itself, because training data is directly or indirectly related to, model performance, model output, model accuracy, and so on. And as I said earlier, I've worked with data, mostly just auditing data over the past years. And again, even within data sets, there is a recurring theme. If you do look at your data, you will always find, either content that shouldn't be there, either like stereotyping content, problematic content, and so on. But before we get even into that, it's important to remember that most of the state-of-the-art models that are, under, that are within big tech's labs, we don't even have access. We can't even look at, we can't even audit, we can't even examine, where the data comes from, what kind of filtering mechanism is used to exclude irrelevant and toxic content. So there is a massive secrecy. So for me, kind of leaning on using anything that comes out of big tech, especially in the context of data and models, where we can't, there is no transparency, we can't replicate, we can't examine it, is a massive red flag, because the pillars of science are really, replication and transparency and the idea of being able to falsify a given statement or claim. So this is important to underscore. So even with, but of course, most data that are used to train, the most popular state-of-the-art models are behind proprietary rights in big tech lab. Doesn't mean we don't get a glimpse of the type of data that's used to train these systems. So there are various open source and public data sets that we have been working on. And as I said, again, there is a massive body of work that audits these data sets. So this paper, for example, looked at, if you haven't read this paper, I highly recommend it. It's called Quality at a Glance, where they looked at about 15 corpora, where they looked at low resource languages. I think they manually audited the quality of 250 language specific corpora related with 5 major public data sets. What they found was that, about 50%, what they found was about 15% corpora have no usable text, and significant fraction contains less than 50%. And most importantly, for low resource languages, the quality of the data tends to be par standard, tends to be really, really low. Again, this relates to, if we are talking about diversity, it's especially in terms of language, it tends to be directly related to low resource languages. So, as well as low quality, there is also the issue of duplicates. So this paper looked at quality within the LION dataset, the LION 2 billion multimodal dataset specifically, and they found that about 30% of the dataset is basically duplicates. So when we do look at datasets, we always find there are massive issues. We also, myself and colleagues have also looked at the LION dataset. This is a paper that was published a few years back, which is relatively old now. We audited the LION dataset. It's a multimodal dataset. This one was, I think, 5 billion image and text pairs. The dataset no longer exists because they're under legal battles because there was CSAM material in it, so it's messy. But basically, what I want to communicate here is that how the data sets, so this is the image part of the data set. I just want to give you a couple of examples. This is a snapshot from the portal itself. So I just typed African here. As you can see, the first set of images that come are a really stereotyping, almost a cliched representative of the continent. Compare that with European, you get, relatively objective representation with just, flags and maps. Again, data sets are, even when, so people at the margins, whether it's, cultures or language or sexual identity and so on, again, tend to be negatively represented or disproportionately negatively impacted by either data sets in representation and models itself. Even when we come up with various methods to detoxify or clean data sets, again, people in marginalized identities at the bottom of society tend to be disproportionately impacted. So in this paper, what Dodge et al., 2022 actually, what they tried to do was they looked at, so the C4 dataset has, I think, about 540 list of words, bad, obscene, blah, blah words that were excluded because they were either sexual in nature, offensive, or so on. So they looked at a sample of those excluded data sets, and they found that words and sentiments that are used, for example, to communicate, sexual health within the queer community, they were disproportionately excluded. Even content coming from, URLs that relate to, African American context and, rap singers and so on, were disproportionately labeled as toxic and excluded. So again, even the filtering mechanisms we employ tends to disproportionately impact identities at the margin. So this is to give you a bigger picture of the dataset landscape. Longpre et al. Have done this massive audit. It's probably the largest audits that I know of, where they audited almost 4,000 datasets of all kinds of modality: image, text, video, audio, and multimodal datasets, and so on. And they have so many, nuggets, but I just want to point out here the main findings in terms of representation. They found that there is a massive inequality in geographical representation, even as datasets get bigger and more inclusive and more comprehensive. Representation, especially from the global south, remains, stable, remains steady. And multilingual representation has not improved by most measures at all. Again, this is a good paper if you are interested in dataset audits. And finally, again, we also want to look at performance benchmarking. Again, the datasets tend to be concentrated, curated and managed by just a handful, either elite universities or big tech corporations. As you can see here, this is from a Mozilla Interneters report. This is the performance benchmarks data that are used across more than 26,000 research papers, and they all come from just 12 elite institutions, including Stanford, Microsoft, and Princeton. So this is again to highlight that there is very little diversity in the training data set, either in the content, but in the curation and in those that are creating the data set. So given all this, the idea of, we'll get to the chip science part, but the idea of using, technologies that stem or that inherently, encode Western values and that penalize any other cultures and values, and anything that stems from that as a vehicle for augmenting diversity just doesn't make sense. And there has been a few critics, especially over the past couple of years, of using synthetic data as a stand-in for human participants or for imitating human behavior. Here is, for example, where they have called the use of synthetic data for augmenting diversity, something that equals diversity washing and consent circumversion. If you are dealing and interacting with marginalized communities, you have to face friction, you have to understand them, you have to gain consent and so on. So synthetic data is just a shortcut to avoid all that rather than to really augment diversity. This is the paper I mentioned earlier where they looked at 16 papers that are proposing synthetic data. Again, here they say that the idea of using synthetic data for diversity augmentation or even for accelerating science ignores and ultimately is in conflict with foundational values of work within human participants, representation, inclusion, and understanding. People have also qualitatively looked at how good synthetic data are in terms of representing reality. This recent paper by Zhou et al., they had various settings, including settings that are kind of high level and abstract, and settings that are really complex and socially salient and much close to messy reality. And the quick conclusion here is that synthetic data might be a good proxy for kind of abstract high-level representation, but not for socially salient, messy contexts. So I will conclude here by saying that, given the composition quality representation of data, given the tendency of large language models where we tend to generate synthetic data from, given their tendency to encode, homogenizing values, Western values, exacerbate bias and so on, the idea of using such synthetic data that comes out of that as something that advances diversity, it's just empirically unsustainable, logically incoherent. But in terms of science, the science part of it, again, the main justification for using synthetic data for science is it cuts cost, and it saves time. But we have to ask, why are we doing science? What's the value of science that we want to cut cost? We want to cut speed. Are we that adheres if we are aiming for cheap science rather than rigorous science that grounds its premises on actual ground truths and what exists in reality. And so again, my conclusion would be, depending on your purpose, it's not to say that don't use synthetic data or don't use or let's stop using large language models, but rather we have to develop a habit of being modest about our claims and about what our models can do. And again, the more we are dealing with complex systems, the more we have to acknowledge that our model might be far from the ground truth, far from reality. And it's really up to us to kind of draw the line where, we might be happy with the trade-off. Hopefully we have time for Q&A, and I'll stop that there.
Let's first thank the speaker. So since we started late, we can take probably about a couple of questions and then save the rest for our coffee break.
Thank you so much. I totally agree that this is very concerning what you have pointed out. I'm still curious also about the question, how much worse are the alternatives in some areas? Because often the synthetic data is somehow trained on real data, right? But this real data has many biases, is really not heterogeneous, leaves out marginalized group to a large degree, and is culturally very biased, let's say, towards Western values. And all of these kind of things are already in the other kind of data sets that we have, right? So do you have an idea of how to move forward, for instance, if we wanted to address these issues? And is it really something specific to synthetic data or more about our data collection in general?
I think the issue for sure is with data and representation in general. Obviously, the more representative, clean, and larger your data is, and if it's curated with the kind of group that you are hoping to model, then the more it reflects reality, then your data has better quality and better chance of representing ground truths. But I think synthetic data is another level. So for me, synthetic data is a model of a model. So you have removed another layer. So there is a massive gap between, if you are looking again at marginalized groups, and synthetic data that comes through churn from problematic data that's then used in models that optimize for Western values and so on. So the issue for sure is data in general, but synthetic data poses another risk, much more immediate and much more a bigger danger, especially in the context of diversity, because it's removed another layer from the ground truths.
Okay, we'll take one more question, and then please have a very long, interesting discussion during break.
Thanks a lot for the talk. It's very interesting, and I definitely the data is sort of one of the main problems. Like the question that I have is, do you know works that also look at the architecture or the learning that also affect? So like my worry is that like even if you go and collect the data that you're missing from a marginalized community, maybe your model is not able to represent it in some sense, or is not able to represent the bimodal distribution of both the center, or something like this. So I wonder, are there works that looking at the architectures also providing, or like is anyone worried about that, or is just not for now? Data is the main thing that everyone is focusing on in the community when looking at these kind of problems.
I don't know. Maybe MT's work is close to that. I'm sure there are works around that that I can't think of one off the top of my head.
We do some of that stuff, so we can chat.
Yeah.
Yeah, and then so questions, please stay for the coffee break. MT has some.
Well, let's thank the speaker.
Thank you.